else, ask them to get their permission ahead of time, everyone who's in the photo. So just a heads up. That goes photos and videos.
That's right. We are live streaming, so I know this is a very tight room. This is highly curated audience, if you will. If you want to share anything, please do so. This is streaming live right now on the Pursuit of Bitcoin YouTube and X channels. And then Ashu, who works on our team, is going to do sort of a highlight reel, takeaways, break everything down, and hopefully have an output in the next week or so. So that would be fantastic as you discuss this topic in the future. If you need anything, content for your reports, etc., we are planning on getting that out. And I think that leads into sort of why we're all here, right? This is such an exciting topic. And when we were sitting around here at Presidio Bitcoin, it also felt like one of those topics that had such a wide variance of opinions, not only on kind of what is the threat, but also what to do about it, who's going to react, how to react. So that was kind of the inception of this event, right? So we really want to have those meaningful takeaways to get the best people in the room as it relates to quantum, theorists, people in industry, Bitcoin developers, people in the Bitcoin industry, software developers, people that are creating products and solutions and presenting ways to solve these various potential threats. And then lastly, who's going to have to react to that, right? So businesses in the Bitcoin space that are going to be downstream, they're going to obviously want to keep their businesses on. What are they going to do about it, right? And how are we going to handle that? So that was the intention for this event, and we're so incredibly excited that you guys are all here. This is absolutely just a fantastic group of people. This morning is going to be fast and furious. We are going to get after it. We have a ton of content. It'll be in this room. We'll have a half-hour break in a little bit, but there's going to be no rest for the wicked, so to speak. At lunch at 12:30, we're actually going to move venues. So thank you to our sponsors, Project 11 and Enduro, for helping us kind of expand this summit. It was obviously very well attended and interested, and that's something that was made with their support, where we basically rented out a meeting facility up the street here called Presidio Officers Club. So we'll have lunch over there. It's going to facilitate breakouts and discussions where we can really get in the weeds. That part won't be live streamed. That is, we have on the back of your name tag a number that is going to be part of the discussion groups, and it's going to be fantastic. We'll have dinner there as well. We have some cryptographers joining us in the evening. It's just going to be a fantastic event. Tomorrow is going to be back in here from about 9 to lunch, and then following that is going to be, hopefully by in the afternoon, you kind of get sun here in San Francisco, a picnic by our friends at Localhost. So it's going to be absolutely fantastic, a couple days events. I'll get off the mic now. Let's get into the content. Austin, let's take it away.
I'm going to do a quick overview of what we're expecting today, and then also talk about a survey that was sent out. So for those of you who like bullet points or numbered lists, we have our goals for the summit. Broadly speaking, 1, demystify and contextualize the quantum threat. 2, explore and advance post-quantum schemes in Bitcoin. That's pretty high level and not specific, so let's get more specific. For the agenda for today and tomorrow, starting with day 1, which is this morning, obviously, we're going to be here focusing on demystifying and contextualizing the quantum threat. So we're going to have a presentation on the state of quantum, rolling into a quantum computing question and answer panel to learn more about various strategies towards quantum computing, also a chance to pose perhaps some skepticisms or doubts for quantum computing. Then after that, we're going to try to we'll transition towards Bitcoin. So what would be the impact on Bitcoin? And then also a threat model analysis. So if a quantum adversary was to come into existence, do they attack Satoshi's coins? What do they do? Then we're going to move into the post-quantum schemes, conversations focused on that. So things like hash-based signatures, various Bitcoin proposals. We got Jameson Lopp, who just dropped something on the mailing list recently. We're going to have a conversation about that. We're going to have perhaps maybe the more standard or more well-known proposals like Commit Reveal, BIP360, and Hourglass. And then after that, for day 2, we're going to come back here, start off with what to do about quantum vulnerable coins. That'll be a panel discussion / debate. And then layer 2, of course, so how do layer 2s play a part of this, like quantum resistant sidechains, quantum resistant rollups perhaps, and then where do we go from here? Taking all the lessons learned from the summit, takeaways, and then moving forward from that. So now let's start with a temperature check. We sent out a survey yesterday and then also a few days ago. I think we got like 51 responses, which out of 70 is a surprisingly good response rate. For the other 20, we might say that your opinion is in like a quantum superposition. We don't quite know what you think, but we're hoping that in a day or two, when you respond to the follow-up survey, that superposition will collapse into a multiple choice answer. For those of you who did respond, we're gonna take a brief moment to go over that. This is the temperature check of the room. So the questions we asked, the first one was, when do you believe cryptographically relevant quantum computers will pose a significant risk to Bitcoin? So the answers were less than 5 years, 5 to 20 years, more than 20 years, never, not a real threat, or unsure. Most people, maybe like 70%, did put a timeline. 50% chose 5 to 20 years. A few said less than 5, and then there was 17% that said more than 20. I think that was pretty interesting. Obviously, one thing to note, this is the temperature check of this room. This is not like the opinion of the quote-unquote Bitcoin space or anything other. This is just this room. 2 brave souls said that it's not a real threat, so maybe they'll make themselves known later and get into some debates. The next thing, which I also thought was interesting, the question was, assuming a cryptographically relevant quantum computer becomes viable, what should we do with quantum vulnerable coins? The answers were nothing, A. Hourglass or something similar, just rate limiting the spending, B. And then C was just burn them. So the responses, 23% said nothing, 31% said Hourglass or something similar where you're rate limiting, 46% said burning. I thought that was interesting because that kind of means like if you look to your left and your right, chances are that one of you 3 wants to burn the coins, and then one of you or 2 of you don't. So if you want to get into a debate, you could just look to the people next to you and probably do that pretty quickly. There will be time for that later as well. The last one was just which approaches should Bitcoin take to defend against a potential quantum computing threat. The first was a native upgrade to a post-quantum signature scheme. This was the majority of people were in favor of this. I think that's not surprising. There was some interest in commit reveal scheme, opt-in layer 2s with post-quantum security, and some people were unsure. So I'm very interested to see, we'll make this also known after, how do the opinions, this was the only one that was not like choose one, you could choose multiple. So after this summit, it'll be interesting to see how the opinions changed towards these. Maybe there's gonna be 60% chose the native upgrade, but then also there's a higher percentage for something like commit reveal or a layer 2. For the no action until a concrete threat appears, we're not like professional pollers here, so that probably was unclear. I don't really know necessarily what a concrete threat was, but this was the result so far. So this is our temperature check. Probably like San Francisco, not too hot, not too cold, just right. And with that said, I've said enough. Let's get Shou up here for our first presentation of the summit, the state of quantum computing. Let's get a round of applause, please. Oh, you just need a fan. Oh, you're good.
Good morning, everyone. So yeah, thank you for inviting me, for giving me this opportunity to talk. So I'm Shou Sugiura, the CEO, co-founders, and CEO at BlockQ Inc. So we are a quantum software company. Do you hear clearly? Okay. Oh, yeah. And let me introduce myself a little bit. So I'm the CEO at BlockQ, but BlockQ is kind of new startup. Like we have founded last year, and before starting, I was a physicist, a quantum computing physicist, and I got research our like Japan Physical Society, Tokyo University, and they're like he's the emperor of Japan, so I got a lot from them. So if you have any question about quantum computing, please ask me. I can answer any question. So let me start my presentation, my talk. So today's talk, I don't go into too much detail about technologies, but I just try to give overview of the quantum technological current status of quantum technology, quantum computing technology. And first of all, why quantum computing is so strong? Maybe you know about this, but superposition is the key. So quantum bit or qubit is a basic unit of quantum computer, and quantum bits can possess many states at the same time. So they can do a calculation they parallelly. Like when we have 10 qubits, we can have quantum qubits pose hundreds, thousands different states, and they can calculate thousands. They can process thousands states at the same time. So that's the power of quantum computing. And at the end of the day, we need to see the result. And interference performs a critical role to get the result. So we do parallel computation, and by using interference, we boil down to one important result. That is the basic philosophy or mechanism of quantum computing. And quantum computing has, roughly speaking, 3 different types. So gate-based quantum computer, and measurement-based quantum computer, and quantum annealing. And gate-based and measurement-based quantum computers are the mathematically equivalent. Of course, the hardware are very different, but mathematically equivalent, and they are universal, which means any quantum computing calculation can be performed by these universal quantum computers. And quantum annealing is a device specialized for optimization, which is not universal. And it was popular, but it's not very popular anymore. And I think the mainstream are these 2 types. And gate-based is the most popular one. IBM and Google and some other quantum startups are working on. But the difference is kind of tiny. So we have circuit, but essentially operations are done by quantum gate operation or measurement. That's the only difference. And measurement-based quantum computation, photonic platform, photonic quantum computing companies are working on measurement-based, and other architecture like superconducting, ion trap, neutral atom, they're working on gate-based quantum computer. So, but building quantum computer is hard. There are many challenges, especially decoherence and gate errors are the biggest bottleneck for us. So first of all, so as I said earlier, qubits can possess superposition. We can process many states at the same time. But this superposition is fragile against noise. It's extremely sensitive to environmental noise, and it will break the calculation. Then we can't do calculation anymore. Currently, gate error is quite good, like 99% to 99.9%. So we only have one error in 1,000 times of operations, but it's still not enough. We need error rate like 10 to minus 10, 20, so it should be extremely good. To achieve that, error correction is essential. So error correction is the technology our community has been working on since 2020, so for 5 years. But error correction is hard because we have making one error-corrected logical qubit consumes thousands, hundreds to thousands of physical qubits. This distinction is extremely important. So naively, error correction is very simple. Like it's just like a majority vote. Suppose we want to encode one to one qubit, then we can just like make 10 physical qubits encoded in which one is encoded. So we just like have 10 ones. Then if you see one is flipped to 0, but you can do a majority vote and correct the error. So this type of majority vote is the essential idea of error correction, but it requires a lot of physical qubit to make up one logical qubit. So this is a distinction. And there are some more hardware limitations, like superconducting qubit connectivity is a problem, like only qubits in superconducting qubits, in superconducting architecture, only nearest neighbor qubits can interconnect each other. So the connectivity can be very complicated, and also there are a lot of infrastructure problems like refrigerator or laser or how to scale up. These problems are, of course, we need the challenges. But these 3 are the major challenges, in my opinion. So let me talk about the tech stack. So By the way, I need to check the time. Okay. So what's the? Yeah. Okay. Sure. So, and let me talk about the technological stack. So, quantum computer, roughly speaking, we have three layers of technological stacks. So, software and middleware and hardware. So, let me start with hardware. There are so many different type of quantum computing hardware. That is one reason. Yeah, that one reason it's confusing to understand. But essentially, as long as we can control states precisely according using quantum mechanics, we can make a quantum computer. So in that sense, superconducting, neutral atom, trapped ion, photonic, and other qubits can be worked as a can work as a quantum computer. That's why there are so many different types. But these four are, in my opinion, the most popular or most promising candidates. And superconducting qubits is the most popular one, like IBM and Google are working on. The advantage is speed. But there's a problem about the stability, scalability, and connectivity. So they have logical qubit, but interaction between two logical qubits hasn't been established because superconducting qubit is installed on 2D surface, so the interconnection is like very limited. And neutral atom and trapped ion are similar structure. They essentially they control, they trap the atom or ion by laser. So it's called laser tweezer, optical tweezer, and they can move around these atoms. So this atom or ion is used as a qubit, and they manipulate these states by shining laser on it. So this is very different technology for superconducting qubit, but as you can imagine, it's very flexible. It has very flexible structure. So speed is very slow, but stability is good, and scalability is also good for neutral atom. So actually, 2 years ago, neutral atom architecture, so a company called QEra realized first error correction, and they already have 10,000 qubits in one physical qubits in their quantum hardware. So in that sense, this is a rising star in quantum hardware. And trapped ion is extremely stable. It's more stable than neutral atom, but scaling is a problem because this is packed into one-dimensional chain, so it's very hard to scale up. So, but once they solve this scalability problem, this is also this is very promising architecture too. And these two are using like atom and ion, so they are which is like most stable material in the world. But superconducting is more like a fabrication. They are making a material to make it work. And photonic is a little bit different. They have very different strategy. They don't have any problem in scalability, but current stage, their error rate is relatively higher than other architecture. And basic error correction has been done in these three architecture, but it hasn't been achieved for photonic. But they have totally different structure. Once they overcome this stability problem, making a million of qubits is easy for a photonic device. They can try to catch up and overtake all these architecture afterwards. That's their strategy. And let me talk about the error correction part. So surface code is by far the most important one. So all the companies are working on surface code, and Google has demonstrated their first error correction demonstration on Willow chip on surface code. But the problem is they consume a lot of physical qubits to make up one logical qubit. Essentially, hundreds to thousands physical qubits is required to make one logical qubit. So that is a big overhead. But recently, most popular error correction code is called QLDCP code. Then they can make one logical qubit from 10 to 100 physical qubit. That is way efficient. So many companies are working on this architecture right now. So seeing the progress of QLDCP code is also important to assess progress of quantum computing. And the software stack, there are many SDKs, and we can make and you can start making quantum algorithm from today, I think. So Qiskit, Cirq, Ticket, QSharp, PennyLane, they're developed by IBM, Google, Microsoft, and so on. So many, all like tech companies are working on this type of quantum computing recently. So they have very easy to use SDK, so you can play around and you can use simulator to see the performance. So let me move on to application. So let me talk about noisy intermediate scale quantum computer. It's called NISQ in short. It was actually a kind of nightmare for quantum computing community. So it was a quantum computer, or it is a quantum computer without error correction. And people expected we have good application using a NISQ device like quantum chemistry or combination optimization program or machine learning. But it turns out that noise is so large that we cannot do any meaningful calculation. So essentially, this project kind of failed. So quantum computing community shift our focus to error correction. So in that sense, it was a dark era of quantum computer. But we do have a clear we do have a clear roadmap towards error corrected device, which is called fault-tolerant quantum computer (FTQC). So this is a roadmap from IBM. You can check out. I can tell you about different companies' roadmap, but IBM has the roadmap towards 2030. So in 2029, they announced that they are making free fault-tolerant quantum computer (FTQC), and they scale it in 2030. That is their roadmap. And before that, they are making a component one by one, like they start to develop QLDPC code, and they make a one logical qubit, and they scale up. That is their roadmap. So of course, there's a lot of things to do, but we have some sort of clear step towards FTQC. And Google already made a one logical qubit like last year by Willow, and some other quantum hardware companies are has slightly faster roadmap too. And so you might think, 2030 is like far away, and last year or this year, we had a buzz about Google's Willow chip and also Microsoft's Majorana chip. So let me comment about it briefly. Actually, Willow is a groundbreaking innovation in our community. So essentially, but this is not like, we don't need to worry about it right now, because this is Willow chip only has 100 physical qubits, and what they performed was one logical qubit operation and successful error correction. So they have one logical qubit right now, but they haven't succeeded to connect two logical qubits, and this is very this requires a lot of complicated wiring, so this hasn't been established yet. Some other platform like Neutral Atom and Ion Trap have already realized that kind of interconnection between logical qubits, but it's still very small. So in a sense, we have logical qubit, but so even though we have 100 physical qubits, we don't need to worry about it because we only have a few logical qubits for now. But scaling up this logical qubit leads to the real quantum application. And when it comes to Microsoft Majorana 1 chip, well, this is scientifically innovative, and but they just made one single physical qubit. But this topological qubit is can have extremely high low error rate, like 10 to minus 10, 20. So logic error correction might not be needed, but they just made one qubit and they haven't performed any operation on that. So in that sense, it's very primitive. So yeah, good to see the progress, and we should observe the progress, but it's I would say it's very primitive.
How is the connectivity between these two?
They just made one physical qubit, and people are arguing about even the existing of qubit itself. So making the operation on qubit hasn't been established yet. So I think, in my opinion, these two are very different. So, and the last part, this is about the application. So this is, we edited a little bit to show the better visibility, but this is from DARPA's results. So DARPA's Quantum Benchmarking Initiative, it's like a government program, and each point represents a different application. And horizontal axis is number of logical qubits required, and vertical axis is number of operations required. So we are currently around here, so there's, I would say, no application for FTQC. And you can see different applications and chemistry and magnetic simulation. They are like quantum analog simulations. They have many applications, but look at these 2 points. These diamonds are decryption. So RSA and ECDSA are not like very difficult program, and especially for ECDSA, it's around 10 to, it's like thousands. So once we have 1,000 logical qubits with enough error rate, like 10 to 15 to 20, then decryption will, so quantum computer will hack the ECDSA. So you can, as you can see, there are many applications, but actually ECDSA is one of the easiest application for quantum computer. So actually this split between RSA and ECC, as I would say ECC, is kind of overlooked in the community, but recently people realize that this is way easier. This is because of the bit length. You know, RSA has 2048 bit, while ECDSA has 256 bit for the same security from the classical attack vector. But quantum computer is doing more like a brute force. Then you know number of combinations are way smaller in ECDSA, so it can fit into smaller quantum computer. That's why it's easier than RSA. So that's the current situation in my understanding. So that's it. So final takeaway is kind of abstract, but you know, as you can see, quantum computing is real, but you know, there are so many things to do, so you don't need to worry too much about it. But at the same time, probably it's not a good idea to ignore it. So because we have, you know, from outside, you might think it's like a hype cycle or like go up and down, but actually inside the community, technological stacks are gradually developing, and once we reach to the threshold, we have real quantum application. So, and looking at the timeline, probably next 5 years, quantum computing hardware companies will set up more concrete roadmap towards FTQC. So that's its best help to assess the progress of quantum computing. Okay, that's it. Thank you very much.
Thank you. I think we might, if there's a super pressing question, see that hand, Max. What is it? What's up?
Thank you. So you talked about how we're going to break ECDSA. RSA has more bits, so it's going to take more time to break it. As you think about post-quantum cryptography, do you think it's always going to be an arms race where we just get more and more bits with new forms of cryptography? Or do you think there's going to be fundamentally like new breakthroughs in cryptography or completely new approaches that are the long-term solution?
From the viewpoint of quantum computing is fundamentally different. So ECDSA and RSA use essentially the same problem of period finding. So we use the same algorithm, but it's vulnerable against quantum computer. But other PQCs use fundamentally different mathematical problem, and there's no known quantum algorithm that efficiently solves the problem. So it's fundamentally different.
Thank you. I'll say if there's other questions, hold them for now. We're about to enter into a Q&A, and there will be also time for those questions then. Let's give it up for Sho one more time. And now I'll invite Matt Pines, there you are, and Terry, there you are, Terry Rudolph. Let's come join the stage, and we'll have our quantum computing Q&A.
Test. Oh, awesome. Well, thank you, Sho. Does yours work?
Hello.
I'll just do some introductions first. So Matthew Pines, I'm an executive director at the Bitcoin Policy Institute. My only qualification for being up here is an undergrad degree in physics and an acute interest in Bitcoin as well. So I'll sort of be play acting as the sort of the skeptic, but also want to tease out some of the more concrete technical milestones that the folks at the front lines of this technology should point us to, right? To pay attention to what are the indicators of the rate of change and the progress, and sort of separate out the noise from the signal. But first, I'll let Terry introduce himself. He's a luminary in the space, a pioneer in photonics, and so I want to give a brief background.
Sure. I'm a theoretical physicist. I was in academia until about 10 years ago, and then became a founder of PsiQuantum, which is a photonic approach to building a quantum computer. And yeah, I guess we're probably now the largest startup quantum computing space based down in Palo Alto.
Excellent. So I'll start off with just a high-level question, almost building off of the last slide there, which I think is pretty much the key question here, which is where are we now on that chart, and how far and how fast do we expect to go to get to that red dot on ECDSA? And that's basically the critical question here. To sort of break it up, evaluating the progress in quantum computing is tough for someone that's not inside the community. I know I've been paying attention to it for a while, and it's not like a new technology. It's been around, theorized since Feynman and David Deutsch, and then it sort of was always 5-10 years away. And so I think people have developed a bit of scar tissue that the sort of hype cycle comes and goes. Is this just another hype cycle? If you're paying attention to the sort of financial news media, you see, quantum-related stocks going on this run, and it sort of seems like it's generating a bit of like a media focus that may be delaminated from the technical conversations that you're having. So just to kind of give me your honest perspective, kind of being in the field, seeing kind of the progress day to day, month to month, year over year. Like, what is the rate of change that you have observed? Do you see that rate of change at a very high level, like shifting? The analogy might be in the AI community, right? There was lots of attempts at generating scalable deep learning models, and it took a few weird tricks. And once those weird tricks were unlocked, true scaling could be achieved by just throwing more data and compute at the problem. And you actually saw these exponentials take off. And so from my perspective, where are we in that analogy? Do we have a kind of a continuous rate of change? Is that a pretty high rate of change? Is it a low rate of change? Is that rate of change itself changing? Like, what's like your perspective?
So an analogy I like to use is the following, and it's a very precise analogy. Imagine you want to make a big block of ice. So you get a big tub of water and you start removing heat from it. The point at which you transition to making ice happens extremely rapidly, exponentially fast. You need two things. One is, if you want a big block of ice, you need a big tub of water, and you've got to just keep continually removing the heat. Now, the thing about fault-tolerant quantum computing is it is exactly a phase transition in a physical system like ice. This is not just like me making up a silly analogy. So if you make a big enough thing and you get your noise rate low enough, then you almost instantly get your fault-tolerant quantum computer. It happens exponentially fast. And so no one has, so I think the Google Willow chip is the only thing you could say that has actually achieved close to that transition. Now, it's done it on an incredibly small system. And it's not just a question of how many logical qubits you need, but it's also, for every logical qubit, you want to ask two questions. One is like, how low is the error rate on it, and how fast can it compute? In the Google thing, they got just beyond the underlying physical error rate of the systems on the chip. So, it's not just a question of take that Google chip and multiply it 10,000 times, which is what we would roughly have to do. They've also got to find a way of getting the noise rates lower, connecting them, as Sho said. Also, there just doesn't exist the large-scale infrastructure to cool them down. But essentially, this is what's going to happen, is that someone is going to transition through this phase transition, and it's going to come just as fast as AI came and hit people in the face.
Sho, your perspective, obviously on the you work a little more on the algorithm side, but you also kind of have to plug and play between the different hardware approaches and the slides that you mentioned there. The wild diversity of different approaches to solving this problem is, I think, overwhelming for someone who's not deeply steeped in this. And if you're just casually paying attention to the developments, you see these headlines, you see the Marjorana 1 announcement, you see Willow. Occasionally a press release will come with some extravagant claim. And I think a lot of that drives the conversation in the Bitcoin space is there's another breakthrough. Is it just around the corner? From someone who's developing solutions, commercial applications, like what do you pay attention to, right? In terms of the rate of progress across these different hardware, solution spaces, and like what is your personal perception of that like rate of change, right? The sort of nonlinearity associated with these different kind of basic building blocks, these sort of core primitives to get to a fault-tolerant, quantum computer. Do you think there's like a few key unlocks? Is it an impossible quest? What's your sort of gut take on how far we have to go?
Yeah. So as Terry said, I think we are on state of like phase transition, but in that sense, we haven't make this type of transition yet because we haven't built the fully scalable FTQC yet. So we have technological components like error correction and like non-transversal, like T-gate, gate injection, gate teleportation, and scaling up. There are some technological components we need to combine, fit into one machine. We haven't succeeded yet. So in that sense, it's very, currently we need to see each component, development of each component. But once we have the one FTQC, as Terry said, error is probably high and size is not enough, but scaling up is more like a continuous transition. So you can see it's more like a predictable phase. But before that, we have to see the FTQC come in our life. So in a sense, to predict when this type of transition happens, we need to see each components and readiness of each component. That's my opinion. And when we talk about the timeline, well, it's very hard to predict, but quantum hardware companies claims like 5 to 10 years they will make this type of architecture. So I think 3 to 5 years probably we will have FTQC, and then we can predict more easily to when the kind of real quantum computer application will come in life.
So this is the $1 trillion question, but just give me your hot take on it. So that other slide you had, which is kind of the matrix of the different hardware-based approaches and their different sort of competitive strengths and weaknesses, and they're sort of optimizing for sort of certain sort of paths to the goal, right? Do you think that like on average over the next 5 years, they will roughly stay close to each other, kind of maybe one takes the lead and with a particular breakthrough, another one catches up, so that by the end of this sort of rough 3 to 5 year time horizon, all 4 of those approaches will still be sort of live contenders for the prize? Or do you see kind of, a possibility that 2 just sort of fall out because for whatever reason they just sort of hit a bottleneck and they don't make it? In terms of monitoring breakthroughs across all these different potential hardware approaches, they have different optimizations, like different paths, almost basic physics to get to the end goal. It's very hard to kind of assess, okay, well, what's the rate of change in that particular technological track? Are they close to getting to the FTQC sort of end game? And do I have to assess all 4 or 5 or sort of hybrid approaches? So like, just how do you from your own perspective evaluate? Obviously, you've made a big bet on the photonic side, so you think that's going to work. But across these different candidate architectures, do you see them all kind of getting to that end goal? They all have roadmaps, but roadmap might be different than what you actually see on the ground.
So, particularly for this community, I would say out of the 4, which I think were the correct 4 to think about, superconducting qubits, cold atoms, ions, and photonics, I would not at all think about cold atoms and ions, because they're just, even if you're incredibly optimistic that they can do everything, the physics of atoms and ions is incredibly slow, and it's limited by, the properties of electrons and atoms that are not going to change. And so even if they build a fault-tolerant quantum computer, it's going to be 10,000 times slower than a superconducting qubit or a photonic machine, or even more than that. So, an algorithm that'll take, say, an hour on a photonic machine, I think the estimates are like 160 days on an ion or cold atom machine. So yeah, they're good for raising funding, they're good for good science. They're good for, and I actually did my PhD in that area. And for me as a scientist, it's just amazing that they did, I did this in the mid-90s. It was just inconceivable that we could do something like that. But if you're serious about like what is an actual computational thread of a quantum computer, you want to know how many logical qubits, what's the logical gate speed, how much power is this thing consuming per logical operation, and so on and so on, the same thing that you do with classical computers. And so I would just say, focus in on the only two approaches that have a possibility of a fast logical gate speed, which is superconducting qubits and photonics.
And do you think those will converge, whether they take different elements of a hybrid architecture? Do you think there's a shot where it's just photonics and you get to the end?
So yeah, maybe I should say, there is a possibility for the cold atoms and ions. It's still very much a far-flung research endeavor to do something where they convert their quantum states into photonics, and then we use fast switches to multiplex them or something. There is some potential roadmap for them to increase their logical gate speed using photonics, but it's very much unproven territory. So then it comes down really to superconducting qubits and photonics. Superconducting qubits, in principle, you can convert the quantum states into photons and then convert those photons into the sort of photons that we can put in optical fibers. And the reason they might want to do that is, well, a very good reason for them to do it, is that photons don't feel heat, and you can't fit all the superconducting qubits you need in one single refrigerator. And so they're going to need many refrigerators, and how do they connect those things? They have to all be quantumly connected and networked. It's very challenging to do it. If you can convert your quantum states into visible light type frequencies, then you can connect them with optical fiber that you can just go down and buy at Fry's Electronics if it hadn't gone bankrupt. So, there is a potential for. Let's say I do think that some approaches for superconducting qubits will go this way. We've sort of just tried to cut out the middleman. We say, okay, we're not going to make the quantum states with some matter-based system and then convert them to photons. We're just going to start with the photons from the start. That has many challenges of its own. But that's roughly speaking, I think, the only two ways I can see to doing really large-scale quantum computing.
Sho, what's your take on that? Agree, disagree?
I have slightly different opinion. I agree about the truly scalable quantum computing. Probably superconducting and neutral atom and ion trap are too slow to do a scalable calculation. But when we think about the RES application, like decryption or some RES application, the situation might be different. That's my opinion. So I feel like neutral atom or ion trap might be something like a vacuum tube, and superconducting and photonics might be like transistor. So because vacuum tube use some sort of fundamental physical phenomena, so that was stable, so we can easily to realize. So first computer was made by vacuum tube, but it's finally overtaken by transistor. So in that sense, probably the ultimate neutral atom and ion trap might not be ultimate winner, but first realization of FTQC might be on FTQC, might be this architecture, and they might reach to the level of RES commercial applications. So that's what do you think?
Interesting. Okay, so you could have this almost like a, maybe double hit where somebody just manages to cross that threshold with some of these different approaches, but maybe that's like their ceiling. And there could be like a lag before these more long-term solutions kind of catch up, and then ultimately that's okay. Oh, sorry. Yeah, we just we'll I think, are we gonna do a Q&A after? Okay, we'll just do 2 more minutes and we'll open up a Q&A. So I want to the shorthand is logical qubits, right? We are at maybe 1-ish, depending on how you count it, and maybe some people have what they debate is a logical qubit, right? It's a sort of ambiguity in exactly what a logical qubit is. But that's the rough measure, is once we get to 1,000 logical qubits, we're in sort of the danger zone, right? And that as we go from where we are now, in the single digits maybe, to hundreds to thousands, that's kind of the order of magnitude sort of step function jumps where the Bitcoin community sort of has to have an order of magnitude more sort of risk perception, right? So we're not clearly there yet. So my question is, if we're sort of 2 orders of magnitude away from the danger zone, what are the most likely triggers that you see that would give us that step function jump, that sort of first one, right? So what should we be paying attention to as the next milestone, breakthrough, something like Marjorana 1, something like Willow's next chip, or something else, maybe another algorithmic breakthrough? Is there 1 or 2 key unlocks that the community is like all hunting for, that if that is achieved, everyone should sort of update their risk perception? Or do you expect it to be just a small series of incremental hardware architecture optimizations, kind of the continuous churn of these different R&D roadmaps? Because obviously the folks in this room can't pay attention to all those different details. And so are there like a handful of big breakthroughs that people talk about at the conferences that are kind of on the horizon, that if we see those happen, we should sort of dramatically update our rough sort of timelines?
Well, yeah, it's Actually, this is I would say this is difficult situation right now because we like 5 years ago, 3 years ago, superconducting qubit is definitely the like a leader of the market. So we just see the bottleneck of superconducting qubit. But now we have many different architecture, like trying to lead to the same goal. So these different architecture has different bottlenecks. So probably we need to carefully assess what's the bottleneck in this architecture. So superconducting, for sure, the connectivity is the bottleneck. And neutral atom, I think error rate is harder to decrease, and ion trap scaling up is a bottleneck, and photonic probably error rate is a bottleneck. So they have different bottlenecks, and we need to see which breakthrough happens first. So that's difficult to assess, but yeah, we need to see carefully. So we need to care about the difference of the architecture. That's my opinion.
So I would look for superconducting qubits. It's kind of like they don't know how to make the big tub to hold the water. If someone comes up with something that a refrigerator that can hit millikelvin temperatures and cool, let's say 100,000 would be an incredible number of qubits. Okay, that would have them within an order of magnitude of what they need. No one has such a thing. The biggest dilution refrigerator being built now at Fermilab is sort of 10 times bigger than the Google one, so maybe can take 1,000. If someone comes up with something that can do 100,000, and that's just a refrigerator technology, go out and ask the people building these fridges, can they do it? That would be something I would go like, yeah, that's a massive step change in what they'll be able to do. For photonics, if someone comes up with a way, so our biggest challenge is not so much noise rate as footprint, like the number of systems. We have this big overhead to do with the fact that the photons don't interact with each other; they just sort of interfere with each other. We, expend huge amounts of resources making small photonic entangled states. There are many other ways of making entangled photonic states. Atoms emit them, ions, quantum dots. There's all sorts of other ways of making entangled states, and none of those are currently good enough to do fault-tolerant quantum computing. They're not reproducible enough, they're not fast enough, they're not low noise enough. But any massive breakthrough like that, which doesn't seem completely unreasonable, that should cause you to update your priors on photonic quantum computing very, very fast. Those would be the 2 sort of engineering type things I would be looking out for.
So that's actually a setup for my last question to put you on the spot here, right? Which is, if you had to pick, 1 year, that's kind of your median estimate for when you think a cryptographically relevant, fault-tolerant quantum computer would pose a material threat to ECDSA. What year would you pick as your, the 50th percentile?
Yeah, I would say 5 years from now, or I don't know, it can be delayed, but looking at the most aggressive hardware roadmap, 5 years is feasible. But if they delay, probably about 5 to 10 years scale, that's the feasible timeline, in my opinion.
And I guess I should ask, could you, give me just a shape of that probability distribution? Is it pretty tight around that 5 year, or does it have a massive tail on either side?
I think it's kind of tight. So we see all the technological stack is ready for FTQC. So making fully functional FTQC will be ready in 1-2 years. If that is successful, probably 5 to 10 years is not a crazy number.
How about you?
Well, you said it's a $1 trillion question, so give me the $1 trillion and you'll get the answer.
We can put some hedges on.
Well, if it's a bet between us, I say 5 years and 1 day, and then I suspect I'm more likely to win the bet. So the biggest changes in cryptographic relevance are going to come from algorithms, I think. Building stuff is slow and expensive. We've already seen, algorithmic development is sort of on an exponential curve. It's not the case that all architectures for quantum computing have equivalent cryptographic relevance. There's some things you can do with the non-locality of photonics you can't do with other architectures, and some of that is cryptographically relevant. So, yeah, I would, it's just not the case that we've been twiddling our thumbs since Shaw's paper and haven't made progress. We've made huge algorithmic progress, and people programming quantum computers now are like Turing with a piece of paper trying to work out what you're going to do with a classical computer. Turing couldn't have invented, important technology like Instagram, could he? So he was just doing stuff by hand. And that's what we're doing with quantum computers. We don't have a quantum computer. We don't really know how fast progress will be once we do. And we're using a bunch of classical computers and smart people to try and improve those algorithms. And it's hard. It's as hard as Turing trying to come up with Instagram by hand. So yeah, I would definitely keep an eye on the algorithm space more than anything.
Awesome. You had a question?
So I was wondering, once a lot of the things that you described sound extremely expensive, like the cooling, the setting up, the inventing new hardware, the setting up big structures of these hardwares. So once people start being able to do anything meaningful in a lab, how long until it becomes economically feasible to do computations? Like, what is the cost of doing a quantum decryption of an ECDSA public key to a private key, and do you have any predictions on like what the timeline would be where that would become something people actually want to do economically?
I think it's already more like an engineering, not academia project. Like, Google has the best chip of superconducting, so it's not like academia project anymore, more like industrial-led projects. So we should keep an eye on hardware companies' progress.
And it doesn't actually cost that much to run any particular compute once you actually have the system set up.
Cost of running it, well,
It's not trivial. You're going to run a cryo plant, and you build materials is very expensive. If you just want to, there's obviously I can't talk through concrete business plans and models, and we do a hell of a lot of modeling of all of this kind of stuff. But no one's going to spend less than 1 billion, and no one's going to spend more than 10 billion to build the first, let's say, few hundred logical qubit quantum computer. And so the cost per logical qubit you expect will go down like it did with classical computers as people get better at, particularly if you're doing semiconductor manufacturing like we're doing, and the cost is, manufacturing and packaging and assembly and stuff. You can sort of predict how it'll go down. And then you just have to say, how many logical qubits does my quantum algorithm need? And is that cost per I need another 50, that's going to cost X amount more. And you can do that kind of stuff yourself. You'll be within an order of magnitude of correct.
I'll defer to you.
Yeah.
Two really just quick things. So first of all, I just wanted to say, from an information theoretic perspective, I think we should also consider, when to be worried. Consider Satoshi's coins move. Maybe that would indicate that someone has machinery powerful enough to solve discrete log or something like that. So I would make that comment. But
I'm definitely on the side of give it to whoever manages it. If you build a quantum computer, you should get it. You should get those coins.
Yeah. And then just quick follow-up to that. What is your opinion on the possibility of a governmental agency or some nation state achieving this technology before industry does, and not revealing the nature of that to the community?
I mean, I can answer part of that. So I did consulting for the government on classified programs, and that's kind of my like high level comment is that the timelines that these gentlemen are stating in terms of the commercial frontier, right? You have to apply some discount factor to where you think the classified research labs, and we'll talk about this in the quantum threat model session in terms of who we think we're actually modeling here, whether it's National Security Agency, whether it's a subset of the PLA, other groups out there. But I think the safe assumption is that governments are probably ahead. But I'm curious, you all, do you think, the governments are that much further ahead? Years ahead or months ahead, or are they actually just waiting for the commercial sector to lead and then they'll just sort of incorporate those breakthroughs?
Okay. So what do you mean by government is ahead? Because as far as I know, in the States, at least in the States, best hardwares are built by academia or companies. So in that sense, government need to access to that. So I think companies are ahead. But when we think globally, the situation might be a bit different because, actually quantum computing race is mostly, roughly speaking, between US and China. And Chinese government found a lot in quantum computing, and they are recently don't reveal a lot of information. So in that sense, this race we do not know. Yeah. But in my opinion, still US has the most advanced technologies, but China tried to catch up. But after 5 years, the situation might be changed.
Yeah, I mean, I totally agree. I don't think in the West there's any chance that the governments have behind closed doors, a more advanced quantum technology. I fundamentally don't believe that. I know a lot of the scientists in government labs, and they're good, but they're not that good. In China, it's a little bit different, obviously, because, well, what's the separation? And at least, I can only speak to the photonics side of things. The lead of the photonics in China, who's the lead of all the quantum computing in China, he and I were postdocs together, actually, in the lab of Anton Zeilinger in like the year 2000 or something. And he's a very nice guy, and I'd love to meet with him. Unfortunately, it's very difficult for us to meet up and talk science. But I can look at what they're saying publicly or what they're doing publicly, and it's state of the art photonics, but it's not somehow vastly ahead of anyone kind of thing. So they would have to also have a massive disconnect, and then somehow he would have to be keeping some big separation between these things and only being public. I just don't think that's probably what's happening. But yeah, I'm no expert in that kind of thing.
So Matt, we're gonna do 2 questions, but I need to ask you to do me a favor. Keep them under 6 minutes in total. So 2 more, we'll squeeze them in.
So Matthew mentioned the name of David Deutsch, and he is the one who basically generalized the Church-Turing principle in, I think, 1985 to quantum computers as well. But he has a different view on quantum computation than most other people, as far as I know. He basically attributes the extra juice that is needed to multiverses or multiverse. So basically my question is to frame it in a Bitcoin mimetic way, where does the yield come from?
Look, I think it doesn't actually matter. David and myself and anyone else, we all agree that mathematically what's the right description of the physics of a quantum computer. We can argue philosophically about how to extract from that mathematics about where and how the computer's being done. But what you have to realize is that a quantum computer is coming because it is just quantum physics, and it is now just engineering. And if any of these quantum computers don't work, that would be far more shocking than, let's say, the Large Hadron Collider having found gremlins coming out of it and black holes or something. Like it's just at least photonic quantum computers, they're derived from quantum field theory. These things are just standard quantum mechanics, and foundations of quantum mechanics and interpretations don't really factor into the question of will they work or not. They will work, or we have to throw out quantum physics, and that would obviously be very exciting. But yeah, I don't know what I would tell the investors. It would be a bit of a challenge.
Yeah, my other degree was in philosophy, and I was very much obsessed with his metaphysical questions of quantum mechanics. And I think if you're curious to sort of try to get at least your arms around some of this, there's a gentleman named Jonathan Garrard who has a useful model of what we think is happening sort of underneath quantum mechanics, where you might see like, where does the yield come from? It comes from a different degree of freedom, right? That if you construct the right types of systems, you're essentially slicing this larger structure. And you can, there's no free lunch in the universe. The universe is computational, and so if it's multi-way, computation, you're sort of stealing from some parts of those computational branches. But the way we are designing these very complicated artifacts is to isolate a certain thread of computation and sort of take maybe from some sort of broadly distributed available computations in the universe and making it useful to us, right? So the universe is seething with potentially useful quantum computations. We're constructing specific circuits to solve problems that are human relevant. So there's not like a free lunch. It's just sort of designing an engine, right? There's energy out there in the universe. It's just not useful for most human purposes until you design the right artifact. That's like my model is. There's actually computation happening all the time in the universe, and we're just sort of engineering artifacts that allow us to sort of extract useful computations out of that sort of sea of computations. Anyways, but that's like metaphysics. Ultimately, at the end of the day, you put a problem in, you get an answer out. If it's the hash or the private key, then it is what it is.
2 minutes, one more.
Yeah. First, thank you guys so much. Like, this has been a really informative and interesting session. Going back to the 5-year roadmap, the IBM roadmap, one of the things that struck me looking at it is it seemed like it kind of took for granted the simplicity of scaling up the number of logical qubits once we figure out how to connect 2 of them, right? It seemed like there's this sort of 0 to 1 problem of like, how do we get 2 of these things talking to each other? And then after that, it's just straight shot to cryptographically relevant quantum computing in 5 years. On the classical side of the industry, I think we've learned over the last 2 or 3 decades that when you start connecting more computers together, you get novel failure modes and you end up with more problems than you started with. I'd love for you guys to just take a minute or so and talk about what are the challenges that we know about with connecting multiple logical qubits together.
It's a
is
fantastic
it gonna be like
question. I'm not
networking
going to
thing?
talk to IBM's
Sure.
roadmap. I mean,
I
it's
wouldn't.
a little bit like a religion or something. But the photonic approach, what we do is very similar to a data center, but it's a data center with liquid helium. It's a bunch of photonic chips being connected by optical fiber, and with some classical control. And the biggest difference being we have some cryogenically cooled detectors. We hire a huge number of people from the supercomputer and data center industry. Like we are building these cabinets and connecting them already and doing this stuff. And this is exactly the sort of thing that those people have been doing for us and modeling for us all the way from the start. I had no clue before, I'm a physicist, I had no clue about that massive set of scaling challenges, and I very, very much doubt IBM do too.
We have time for one more Hunter Beast. I see him.
Can you keep it under a minute? Okay. As Matt mentioned, there's no such thing as free lunch, so the time we're spending here is coming from your break later. I'm sure you'll be happy with that. That's fine.
So my question is for Terry. I see you building your blueprint architecture. You're actually going for 99.99% error correction codes. You're building suspiciously scalable hardware in that it looks almost like how a Bitcoin miner might scale. And so I got to ask. It looks so. How would you say? I just got to ask. Do you have plans for quantum key recovery? And if not, what's keeping you from doing that?
We do not have plans, and we do get a lot of inbound interest from many sectors of the world, and mainly AI, for our hardware and for sort of classical uses of our hardware. But the quantum side of what we're doing is hard, and that's what we're focused on. And there's no. You can't hide this stuff as well. It's a company of hundreds of people, right? It's not like we're going to start putting out. Yeah. Anyway.
What would you say? Why would you say? Because your hardware could be capable of doing that. So I'm just saying, like, what keeps you from doing that?
So if you're talking about could we use it for classical stuff?
No. For
the quantum side of things, it's still you need a bigger machine than we're currently doing at lower error rates than what we currently have. But those are the sorts of things that are made as strategic decisions in a company that people you have to sit down and say, is this something, and who you engage with in both the government and other commercial sectors and so on. Those are all strategic decisions that are made. They're not obviously things you necessarily say publicly, but they're also not, you've got a board and hundreds of people and so on. Like it's not stuff which I think you should be too cloak and dagger about. Yeah.
I think what Hunter's asking is, once you have a computer that does, will you take bitcoins?
All right, with that said, I'm going to jump in. We're over.
Yes.
We're over. We got a jam-packed schedule. There's plenty of time later to continue these discussions over happy hour and food and views and all that good stuff. Let's give a round of applause, please. And welcome Clara up. As a quick reminder, we have this presentation with Clara, and then we have a break. It's a short break because we just had some extra questions. If you can hear me, clap twice.
Okay.
It kind of works. All right, everyone, let's give it up for Clara.
Yeah. So hi, everyone. We heard a lot about quantum computing, but what we actually care about is Bitcoin, and is somebody going to steal it, as we heard earlier. So my presentation is based on a report we wrote together with Anthony that just tries to put a baseline on quantum computing, its relation to Bitcoin, and pretty much where we are. Cool. Okay. So we're going to talk about signatures, we're going to talk about mining, we're going to talk about the threat model for Bitcoin, and timelines for solutions. Cool. So when we're thinking about quantum computing and Bitcoin, there are two topics that come to mind. First of all, mining. What if we have a quantum computer that will run probably right now Grover's algorithm efficiently and is able to compete with ASICs? And when we're thinking about mining, we're thinking about a cryptographically relevant quantum computer, CRQC. You will hear this pretty much throughout this day and the next one. And we're thinking about the quantum computer breaking cryptographic assumptions in the context of Bitcoin, elliptic curve cryptography. We already saw these three letters meaning something else, but I'm sure you can get it from context. Cool. So mining. We all know in mining, we're trying to find a nonce to hash below a given target. When we're thinking about classical mining, what we have right now, the way that this works, we have more attempts, the higher the probability we find this nonce. So we can think about a box. We push the button, we look inside, did it work? No. We push again, did it work? Did it work? No, until it does. It grows linearly, and you can do this in parallel. So Alice and Bob can have their two boxes, click on them, look, click, look, click, look. They can also do this together. It doesn't matter. When we're thinking about quantum mining, the box looks very different. We click, 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 and with each click, the probability of when we look inside, do we see the solution, goes up. So we click at it, it goes like 50, 55, 60. At some point, we get to a number we're comfortable with. We open the box, and we see if we found the solution or not. There's like, the math was done, the optimization, how many clicks until we look inside, what's the best choice. But although it sounds like click and find solution, there is a deep difference coming from the different structures. So the good news for a quantum miner is that theoretically we have a very significant speed up. The not so good news, at least for us, is that you cannot do this in parallel. So if in classic computing, it doesn't matter if Alice and Bob have their separate boxes and they're clicking, in quantum computing, it is much more efficient for both of them to put their efforts together and use the same machine. So it's very difficult to do this in parallel. And if it makes you ask what's up with centralization, this is a very good question. So the good news about mining is that it's not happening anytime soon. The name of the game in mining are those clicks. It's the clock time. ASICs are very, very, very good. And quantum computers are not really a thing yet. But when they will be, still we can expect them to be significantly slower, much less stable. So not in the coming decades. This is not coming up. If it will come up one day, we should be worried about centralization, where we'll see more stale blocks when you do the game theory of your optimal strategy. And once you have stale blocks, you have problems with your security assumptions. So where we are right now with mining, lots of interesting theoretical questions, lots of things to think about. Do we have a different proof of work algorithm? But absolutely not something to lose sleep about, just because of the engineering being so difficult and ASICs being so good. Cool, so if you do want to lose sleep about something, let's talk about cryptography. We all know asymmetric cryptography. We have a public key that is, well, known to the public, and then we have a secret key, which is, well, secret. And with the secret key, we can use this for messaging, but another thing we can do with this kind of schemes is sign messages. So you can use your secret key to sign a message, and then everybody who sees the public key can check the signature. And we have some very, very basic cryptographic assumptions that a lot of things, including Bitcoin, are built upon. So calculating the public key from the secret key is easy. You come up with the secret key, you find it. Doing the opposite operation, and this is where the asymmetry comes from, calculating the secret key from the public key is infeasible, takes as long as the age of the universe, and so on. It is not a thing. And also, when we're talking about signatures, forging a signature, if you only have the public key, is also infeasible. Okay? Good. So this is the world we're living in, and this is what Bitcoin and so many other things are built upon. So let's say we have a CRQC. What will the CRQC break? Everything. It's a big problem. So there is a small caveat, but all in all, just from the definition of a cryptographically relevant quantum computer is that it breaks ECC and later on most of classical current cryptography. So what actually should or could happen is that calculating the secret key from the public key becomes easy instead of infeasible. And then Bob's your uncle. You can do whatever you want because you broke the very, very basic assumption of cryptography. And in Bitcoin specifically, you can forge a signature if you see the public key. If you have the public key, you get the secret key, and then you can do whatever you want. The one thing that gives us some grace in this context is that you need access to the public key. You do need to see it to do something with it. So here we are at Bitcoin. Okay, so as, again, you're sending a Bitcoin transaction, you need to sign with the secret key associated with the public key of the UTXO, and then they check it, so on. In some cases, for some addresses, the public key is present on-chain. It's lying around there. Anybody with a handy CRQC can pick it up, derive the secret key, and go forward. In other cases, the public key is hashed. This means that they cannot, or a potential quantum attacker cannot start the process of deriving the secret key from the public key because it's hashed. And then when somebody wants to spend it, they do need to present the public key and the signature. And then to validate the transaction, you check the signature with the public key, and you check that the public key hashes to whatever you see on-chain. Cool. So we have that, and this is all in all the quantum problem when it comes to Bitcoin. Cool. So about this, so as we said, some signatures are immediately vulnerable. This is what we call the long-range attack. These are the signatures that either show the public key on chain or the public key was leaked for different reasons. So these are examples of the signatures, and in a later talk we'll see some numbers relating to how much funds and how much UTXOs are using these types of addresses. But then, as I said, you need access to the public key, and sometimes it doesn't come from the address type, it comes from address reuse. Do not reuse addresses. Thank you. If the excuse you need is quantum computing, sure, take it, but this is a very, very bad practice in general. And then, again, there are some numbers coming up. A lot of the public keys that are available to whoever wants to take them come from address reuse. Pretty much any other UTXO will become vulnerable upon spend. This means that whenever you're trying to spend this UTXO, as we said earlier, you present the public key, it's compared to the hash, and the signature is checked. And from that time, anybody with a CRQC can go ahead and try to derive the secret key. We call this short-range attack or upon-spend attacks. And I'll take a second to talk, the timelines of these attacks are very, very different. In a long-range attack, you have pretty much all the time in the world until whoever the owner tries to spend it, succeeds, and so on. So in the long-range attack, you can have days, weeks, years, whatever. In a short-range attack, you have, let's assume it goes through the mempool. You have the time from the UTXO appearing in the mempool and revealing the public key to the UTXO going on the blockchain and maybe potentially a few blocks in. Okay, so the attacker can try to send a competing transaction. And if we're talking about very, very large sums, we can consider some reorg of the chain, a block or two, but still you're talking like hours, days, not all the time in the world you will see in a long-range attack. And this is also like very clearly triggered if somebody spends it. If your public key gets leaked in a different way, that's a different problem and can change the time estimation on the attack. Cool. So not all signatures will give us these problems. Not every signature scheme can be attacked by quantum computers. So we already know a few quantum secure schemes that were suggested. It's a very popular and deep research topic. The problem with most of the schemes is that something has to give. So it's usually either the efficiency, the functionality, in many cases, both. And in general, the reason we trust elliptic curve cryptography, RSA, whatever it is that a lot of very, very, very smart people tried to break it and they failed. And what happens with some of these quantum secure schemes is that they get published and then very, very smart people try to break them and then they break them, occasionally with a classical computer. So it's not like theoretically something will happen, no. So when we're thinking about cryptographic schemes, first of all, they need to offer efficiency, they need to offer capability, but they also need to mature. Like some people need to give some hits about it, we need to think about this, and then we can move forward. So honestly, when we're thinking about these kinds of schemes, the longer we wait, the better, unless we miss the train, and then that's too bad. This is a very active, ongoing research area outside of the scope of Bitcoin. Lots of funding, lots of grants, lots of PhD, lots of tenure tracks, lots of prizes. This is happening right now. And to some extent, we can sit and reap this fruit and look at the environment as it moves forward. Yeah, let's have a question.
Yeah, I just had a question. I mean, in light of what you said, that the longer you wait before you draw something, and in light of the timeline set for a computer, is it realistic
So I think we'll have a lot of deeper conversations throughout the day, but even when like lattice-based, for example, hash-based, these are families of things. So usually, like in all of the examples that I'm aware of, it's not like a whole family was brought down. You're basing, if you're going to classical things, you're saying, okay,
do you think, practically speaking, that would be an alternative to consider?
It's maybe. This is a word that I think we should be using more when you're talking about quantum computing and emergent technologies. It could be. It could be that an amazing scheme comes out tomorrow, and then we discover the timeline for quantum computers is not in 5 to 10 years. We discover it's in 20 years. So it has time to mature. We're looking at it, and then when we have to choose, this is the choice that we take. So could it be? Yes. Do I want to bet money on this? I'm not a betting person. So, there's a saying that I really like, which is prophecy is given to the fools. So I'm trying not to prophesize, but we'll just have to read the environment, see what is going on, and make decisions as they come. Sure. Great. So we chose something. We have the signature. We need to move. All of the we need to move UTXOs from this unsecure addresses and migrate them to this new and secure. So we'll talk a lot in the upcoming days about how are we going to do this, but just to sort of set the scene, let's talk a bit about numbers, and we'll have a deeper dive about this later. Where the current UTXO set is around a bit short of 200 million UTXOs. That's quite a lot. About 60 million of these UTXOs expose public keys for various reasons. So the 60 will be, I guess, more stress to move. But if we're in a world where CRQCs are a thing, all of these addresses need to move to something secure, and that is a lot. We all know Bitcoin, throughput, limited block space. This is something we need to keep in mind when we're thinking about the Bitcoin threat. We found a solution. Doing the last step of moving towards the solution is time-consuming, and we need a good amount of preparation to do this. So the estimates for migration go from 3 months to 3 years. Of course, there's no upper bound. It can take forever. But the 3 month is based on we're stopping everything and we're just moving UTXO. Nobody does anything else. Not very realistic, but maybe if everybody's panicking. And I think a better way maybe to think about it is allowing for some organic migration happening. Say we have a standard, we're thinking it's coming, and then there's a lot of UTXO activity just happening. So there's nothing stopping us from moving it to secure addresses and so on as time passes by. And this will make these estimates even shorter, but this again assumes that these UTXOs have anywhere to migrate to. Cool. So we talked about migration, we talked about timeline, but at the heart of a CRQC, this is a security bug. This means we have built Bitcoin on some assumptions, and now we discover that one of the assumptions doesn't work. Somewhere in our, we can think about other security bugs. We thought that the computer is going to do X, and now it cannot do this anymore. What do we do? What do we do with these bugs? How do we deal with it? And this is, unlike a lot of the previous discussion that is more technological, this is more philosophical. So where's the philosophy guy? But still, what do we do with addresses that do not migrate? And of course, we don't know if they don't want to, they can't, they lost the keys. We know what's happening, but there are coins that did not move, and we see CRQCs hanging out around us. So there are, at the two ends of the spectrum, we have the burn philosophy. There's some deadline. after this block height, anything that could have, any UTXO that could have been created by CRQC is rejected. This means that a lot of coins, or some coins, again, numbers coming up later today, can never burn and can never move, and they're considered burned or frozen, depending what you like. And this is a deep philosophical clash with how we think about Bitcoin. On the one hand, on the other hand, I don't know if Bitcoin was ever to, I don't know. We'll talk about this later. Cool. I do have opinions, surprising. Cool. On the other side of the spectrum, we have the still philosophy that, well, anybody, you get a CRQC, you can break the cryptography, good for you, enjoy your brand new shiny Bitcoins, and yeah, go to town. This means, I think there's no way around it, this will destabilize the ecosystem, even more so if whoever steals this Bitcoins goes like, well, this is not such an amazing system. If everybody can come in and steal this Bitcoin, I'd better go ahead and sell them. But whatever will happen will have a very, very significant effect on the ecosystem, and this is something we should be thinking about. So these are the two ends of the spectrum. Of course, there's a lot in the middle, and I think we'll be talking about this a lot in the upcoming days, months, years, until we'll come up about with a solution or a different discussion topic. But this is, I think, the deeply philosophical question that CRQCs bring. Okay, we talked about the steps, the questions. Let's have a bit of a timeline here, because we talked about timeline for quantum computers. What is the timeline for the Bitcoin reaction for it? We're thinking, when we're thinking about this, about three phases. We're thinking about research, we're thinking about implementation, and then migration. And there are, at least in our mind, two paths. One is the long-term path, which is pretty much where we are right now. We're thinking that there's like half a decade ahead of us. We have time to think, to consider, to wait for schemes to mature, to do extra research, to test things very carefully. But then there's also the path where we're moving to contingency. We're looking around the corner, we see CRQC waving back at us, and we're like, okay, something needs to happen, we need to move. And of course, we can jump from one to the other based on what we see around us. And all of this is based on things like SegWit, Taproot, how things moved earlier in Bitcoin. So these are our guesses. So for research, like if we're taking our time to deeply think about it, let schemes mature and so on, something like 2.5 years. If we're in a hurry, in 6 months, again, probably less, but this is a good estimate of we need to act soon. When it comes to implementation, testing, again, doing everything very careful, something like 1.5 years. If we're in a hurry, you can do this in a year. Honestly, some of the people here in the audience can like slap it together in 3 days, I think. But even if we're in contingency mode, we're stressed, we probably want to be more careful with this, so let's put 1 year on it. And then migration, so 3 years is a reasonable estimate. Some organic, some people are moving just for the sake of security. But then if everybody wants to move at once, let's put 1 year at this. Again, like the shortest estimate I've seen is talking about like 75 days, but that's, a lot of it also depends on the scheme we choose and so on, but these are somewhat realistic numbers. So all in all, if we have the time that we think we have, 7 years is a good number. If we don't, it can be cut down to 2 years and probably even less, but then, you know, it's risky, lots of money in the system and so on. So if we'll need to move from long-term to contingency, we still need to be somewhat careful not to mess everything up. Cool. And one more subject that I think we're not talking about enough. Bitcoin is not an island. It uses a lot of infrastructure. It lives on the internet. It uses things around it. And then we need to know that all of our dependencies, all of the libraries, all of the things that we're using, they have this figured out. So there is a lot of, like, we're not the only ones in the world that are worried about quantum. There is a lot of work going into this, but this is always something to keep in mind, that whatever that we're using outside of the Bitcoin ecosystem is also secure. They're not messing up, they're not using some weird schemes that were broken, and so on. So the internet, there's some peer-to-peer level attacks. It's very fashionable in academy, various variations on Eclipse attack, BGP attacks, and so on. A lot of it has some cryptographic assumptions at the bottom of it, of somebody signs something, somebody says something on the path, and so on. We want to be always aware of these kinds of things. And of course, there's other outside, like for example, a new core version comes out, it comes out with a signature. What is the signature? What is the signature scheme? Where does it come from? And I bet there's a lot of other things in the ecosystem around us that once we face a worldwide security bug, we want to make sure that any connection that we do, we remember that this thing is in the background and we should be watching out. Cool, so we talked about the Bitcoin threat model, we talked about mining and signatures, we touched on the burn versus steal philosophical dilemma, and we'll touch about this some more, and we talked some about the timeline to solution, and you're more than welcome to read the full report here. Yeah. And I'm looking forward to all of the discussions that are going to come up.
Let's give it up for Clara. All right, so now we are starting a break. You have about 20 minutes. We're going to be back at 11 for more content. 3 more fantastic conversations before we make our way over to the second venue for lunch. Do what you got to do. Caffeine, bathroom, more caffeine. We'll be ready to go.
that time. Let's go. We have a few more talks here in this building, and then the whole afternoon is dedicated to discussions and conversations in breakout groups. There's going to be ample time to chat with all the amazing people that are in this room. We have just a couple more talks because we really wanted to set the stage. We really wanted to get a foundation for everyone around quantum, around Bitcoin, that'll feed into those breakout groups. We also have like an hour and a half lunch coming up, so there's plenty of time to mingle. Grab a coffee. Hani is still here pouring matcha. He will be leaving shortly. Please do get a chance to try it. It's fantastic. He will not be here tomorrow, so take this opportunity. We have tea back there, coffee, yerba mate. What else? Green tea, black tea. Water.
Yeah, water.
Izzy's. I'm sure that we have a ton of different types of caffeinated beverages. I think there's a Celsius hidden somewhere. If you really need that, raise your hand. I can get that for you. We want to amp this up. All right. I'm going to start calling some names out. Please make your way on over. I see you. Like I said, we will be going to lunch here just up the road at Presidio Officers Club. Plenty of time to continue the fantastic conversations, but we want to get started here. All right, fantastic. Thank you so much.
Hey.
Take it away.
No worries. Hey, everyone. You're wondering who I am? I'm Anthony. I co-authored the report with Clara, the chain code report. And this is actually my first Bitcoin event. So I do the BitDevs in Perth, Australia, but I've never actually been to such an event. So a bit of an exciting time for me. So Clara was referring to some numbers and trying to scope what the problem is. What is the vulnerable Bitcoin sphere look like? So I'm going to present some of that information and hopefully can inform some of the following conversations. I've got a bit of a Frankenstein setup here, so just bear with me. Okay, so the main motivation for this talk is to really establish how much Bitcoin is immediately quantum vulnerable and why is it quantum vulnerable. So when I was writing the report, I came across a number of figures, quotes for people to try and establish what is the risk of immediately quantum vulnerable coins. And that's coins that have their long-range attack, or they have public keys exposed. So 5 to 10 million, very precise number. That's from Project 11, that's 6 million. 25, 20%. So what is it? So this is what I was looking to establish. Okay, so broadly speaking, there's probably 3 sources of quantum vulnerability. And I'm going to be looking at what they look like roughly now and what they've looked like through time. So we've got the address reuse problem. So those are the revealed keys and scripts. We've got the inherently vulnerable script types. So pay to pub key, pay to multisig, and pay to taproot. We've got fork exposure. So I'm only focusing on Bitcoin Cash, but you could go further and look at SV, Gold, Diamond, all those forks. But we focus on Bitcoin Cash. So that's the first part of what I'm going to be talking about. The next part is the vulnerability assessment. So I know some people have shown figures around the top 10. Jameson Lott's done this. I looked at the top 1,000 just to see what things look like when we dive a little bit deeper. And also, what are some implications for the migration efforts or the burn and steal decision conversation? Okay, so this is the headline. So it's a bit higher than what Project 11 came up with. It's about 6.5 million. And that's 32% of the total supply, the current supply. 70% of that is address reuse. So that's a significant problem. And as Clara was saying, and some of the cheers, don't reuse addresses, all right? The inherently vulnerable coins, so that's about 1.9 million, 30% or so. Overwhelmingly, that's pay to pub key. Pay to taproot is a growing cohort of that. And pay to multisig is only actually 69 Bitcoin, so it's tiny. Then we've got some exposed from fork. So that's where we have the spends on the fork, but they still remain as UTXOs on Bitcoin. That's only about 150,000 Bitcoin. And a lot of these figures that I'm presenting is block height 900,000, which is in early June. So just to clarify what address reuse is, that's when we have at least one spend, but there's still UTXOs associated with the address. And we're only looking at the hash script types. So that's the pay to pub key hash, pay to script hash, and the witness versions of those. So we already have the exposed keys for pay to pub key, so we just carve those out of the analysis. This is very visual heavy, so I've got a lot of visualizations in the talk. Okay, so what was the methodology? So we went back about 10 years, or a bit more than 10 years, from block height 400K to 900K, and in 50K increments. And we basically reconstructed the UTXO set, and we're looking for UTXOs that had associated with reuse addresses, the vulnerable script types, and just generally trying to understand what the UTXO set looked like at those various points. And then when we did the Bitcoin Cash fork exposure, post the fork, we look for which TX outputs have been spent on cash but remain unspent on Bitcoin. And then we only consider the marginal contributions, so don't try and double count things, I suppose. And so I did this analysis in Google's BigQuery, so there was some quirks involved with those data sets, but that allowed me to sort of scale up these numbers and combine the two data sets. And I believe, I don't really know how large I would have liked to look at SV just because it's a novelty, but I think that blockchain's in the order of terabytes, so I wasn't going to do that. All right, so this is what it looks like from the 400K to 900K. So the below the line, the red line represents the sort of the Bitcoin only exposure, and then the pink bars represent what the Bitcoin Cash fork exposure looked like. So as you can see, after the fork, a heap of people dumped their cash, but they still kept their UTXOs unspent on Bitcoin. And then over time, people have transacted on Bitcoin and reduced that figure. So what we're looking at the moment, 6.5 million, but it has been increasing recently, and we'll look at why that is. This is just another way of spinning the data, so breaking it down into the various constituents. So although I said we've got 3 categories, I've broken out Taproot from that inherently vulnerable script type. So we've got the red, which is the pay to pub key and pay to multisig. The teal, which is the pay to Taproot. Then the reused, the sort of the hashed coloring, and then the cache at the pink at the top. And as a breakdown, as percentage of the total volume of quantum vulnerable, this is what we're looking at. Okay, so I'm just going to now dive into some of the address reuse aspects. Just some caveats up front. So maybe not all of the script outputs are immediately vulnerable. There might be some non-signature mechanisms there, so I haven't been able to tease that out yet. But I've just assumed that the majority of these types are like exposed pub keys due to their use for multisig and the like. Okay, so address reuse is a growing problem. Surprisingly enough, I think we've been talking about it in the community for many, many years, but it has escalated, and it has had some periods where it's in particularly blown up or increased. So between block height 500 and 550, perhaps that was that first like retail wave and the first adoption wave. People weren't using good practices. People were just sort of YOLOing into the space. And perhaps the exchanges had their operational procedures. They weren't really what they should be, and maybe still aren't. But maybe that explains the huge explosion from 500 to 550. And then more recently, it's sort of been gradually increasing, and I'm guessing that it might be to do with ETFs and the financialization side of things. So it has definitely been on the increase. And yeah, we need to get the message out there, we need to stop reusing addresses. Like, let's get onto this, and we can really make a dent in the volume of coins that are quantum vulnerable. So just had a bit of a look at, I guess, address reuse and UTXOs sitting in those addresses. So just a definition of the unique address, that's an address that has at least one UTXO at each block height. So it's got value holding within that, against that address. An address reuse is the percentage of those that have been reused. And then the UTXOs in the reuse addresses is the percentage of UTXOs that belong to a reuse address. So I'll just talk to it. So we currently have less than 20% of addresses that are reused, but overwhelmingly they hold 60% of the UTXOs. A majority are single use, which is good, but what's this saying is that when people reuse addresses, they reuse them aggressively, right? So a minority of the addresses account for a majority of the reuse. And this is just looking at, again, over time, to see what the trends look like. Massive escalation. Okay, so moving on to top 1,000 addresses. So this represents about 6 million Bitcoin, so 30% of the supply. The first address, which is Binance, holds 250,000. And the 1,000th address, which was unlabeled, had 1,700. So in that 1,000, there was almost 30% reused, and those represented 2.73, and that's like 45% of the total holdings of the top 1,000. This was from the resource that a lot of people refer to, the rich list, and we do use the labels there. I guess there's a caveat here that these labels probably have been derived from the fact that when an address is reused, we can get some information about who it belongs to. So there's probably a bias to having these addresses like labeled because they are reused, and so ones that aren't reused, they still probably belong to an exchange. We just can't confidently identify that to be the case. It's not public knowledge. Okay, so this is the top 10, and of those top 10 addresses, yeah, it doesn't look great. Bit of a worry. They're all labeled except for one of them. Yes, thanks. Stole it. Jameson, thank you. So now looking at the, of the top 1,000, picking out all the labels and organizing them together and associating them with particular entities and getting a breakdown of the funds. So Binance have a number of addresses in that top 1,000, representing 600,000 Bitcoin, and 500K or so is reused. And there's heavy reuse across, again, there's a bias to this, but there is heavy reuse across the exchange holdings. There's like notable absentees from these labels like Coinbase Prime and the like they obviously have some better practices than the rest of the industry. But yeah, it's a bit of a concern that we have this sort of behavior from some of the leading companies in the space. And this is just a breakdown of looking at, for the top 10 holdings associated with each script type, like how is their reuse and who do they belong to. It's across, I guess, all script types. It's a problem no matter which, I guess, operational procedures you're using or companies are using. Okay, so so what are the implications of some of this for the burn and steal decision, the dilemma? Well, we've got three main sources of the quantum vulnerable. We probably can consider the Bitcoin Cash stuff happened 8 years ago now. Maybe most of those can be transacted. They're still active, so maybe they can be still moved today. I think that's maybe a fair assumption. So probably we don't really need to worry about those 150K. They can probably carve that and say, look, that probably is not truly quantum vulnerable. If people want to transact, they probably can. So we'll set that aside. For the reuse side of things, what does it look like? Like, can we kind of put some bounds on that? And the way to do this, we're just looking at last activity as like some measure of can this stuff be moved, right? So I guess as the bias, the longer things have remained unmoved, the more likely they are to be lost or unmovable, unspendable. And so we're just using this as a yardstick to work out, okay, can these be moved possibly? So this is looking at the reused addresses and the last activity of when there's been last acted, like a transaction against an address. Thankfully, a lot of the coins are regularly transacted recently, and so since block 850, that's like 94% of the holdings of the reused addresses. So just a recap, like so 4.5 million are reused, so about 4.2 million are very recently moved. Maybe if we go back beyond 10 years, that represents only 50,000 coins. So coins that haven't moved in 10 years from the reuse side of things, it's small, it's negligible. And so maybe with reuse addresses, there's, again, people can actually transact with these, that they're potentially spendable. And if push comes to shove, most of these coins will become non-vulnerable. Okay, so this is just a bit more of a breakdown. Probably, I mean, you can challenge me on this, but I think that this is probably the best way we can think about it. Maybe most of the the reuse addresses, they maybe are also movable, can transact with them. Okay, so what about the inherently vulnerable script types? So pay to pub key. This is a separation of what transactions are coin-based transactions and what are not. So what has been mined and what was actually like an organic transaction. And overwhelmingly, they're block rewards. So new UTXOs are not being created, though maybe there was one in the last few weeks or so, I think someone pointed out. But largely, there's been no activity for some time. They've obviously got significant value, and it's like historical, I suppose. So what about pay to multi-sig? Yeah, so this is interesting because they're actually, surprisingly enough, being created quite regularly, but the value is tiny. So it's 69 Bitcoin, but like 2.5 or 2.2 million UTXOs.
They're all stamps.
Yep, they're all data carrying alike. Is it stamps? Okay. So do we need to worry about this? Yep. This is another interesting one, pay to tap rate. So both growing in number of UTXOs and Bitcoin encumbered, but still at the moment, it's only 150,000 coins. UTXO size, it's kind of big. We'll talk about that in a moment. And also most of them are key spent. So this is from B10C's Mainnet Observer, great resource, lots of beautiful visualizations, so check it out. But certainly key spend path seems to be the favored route for these. And I guess BIP360 is proposing to remove that. So it's something to be aware of, that this is how most people are using pay to tap rate at the moment. So there's going to have to be some behavioral changes or... Yep. This is just something to be aware of. This is how it's being used, and that's we're talking about cutting that off, right? So also this comes from that UTXO set report that Mempool Research did, and most of these 60 million or whatever it is, they're uneconomical UTXOs, So they're tiny. They're between 0 and 1K.
They're all over the dust limit, and now that we're dropping the fee rate by a factor, they're much spending.
Okay, so they are economic now. Right, so let's see what happens then.
So all of these are above dust fee rate, and since the mempool cleared in February, now transactions are spendable again at 1 sat very reliably. It clears like every day. And recently we've seen that about 28% of the hash rate is mining transactions that use even fee rates below the prior default minimum relay transaction fee rate of 1 sat per vbyte. So there's been recently a little bit of debate on a pull request to Bitcoin Core that drops the minimum relay transaction fee rate to 1/10 of a sat per vbyte. And so a lot of these UTXOs were created in the context of ordinals or inscriptions, and they could be collected, especially at 1 sat per vbyte. It would make sense to collect them. There's a lot of small amounts tied up with there that would, if you consolidate them, amount to something. But if the fee rate drops to 1/10 of a sat per vbyte, then that is, well, really worth doing. So we've been seeing a bunch of transactions sitting in the mempool queue below 1 sat per vbyte, consolidating these 296 sat per vbyte pay-to-taproot inputs at like thousands of them in one transaction. So this cleanup is happening a little bit. But still, the year-to-date trend is that pay-to-taproot is up in count by like 50,000 UTXOs. So even while all the tiny stuff is being now a little bit consolidated, we still have more pay-to-taproot outputs than at the start of the year.
And then they'll just go lower, right?
The average value goes up.
Okay, so what does this all say about what the situation looks like? We probably already all knew this, but paid pub key is the real problem. So it's almost 9% of the current supply, and don't want to idolize anyone, but like this is what Satoshi said about lost coins, and maybe these are lost coins. Pay to multisig, yep, stacks, got that mixed up. And pay to taproot is a secondary issue. It's a small but growing share. Generally KeePass spent, and some relation with our BIP360 there. Okay, so although we have this headline of 6.5 million that is immediately quantum honorable, and 4.5 million of that is address reuse, and probably most of those can be moved as spendable. And then we have that top 1,000 to be more egregious reusers than the general population. We've got the fork exposure, 150,000. Probably most of those can be moved as well. So maybe we don't need to worry about that. Pay to pub key is a problem. Probably they're not going to move. And then we've got the pay to taproot, KeePass favored, BIP360, all that. So if we round it all out, it looks like maybe of that 6.5 million, we have more like 2 million that were a cryptographically relevant quantum computer to land. That's what it looks like. The other stuff probably can be moved. Okay, so this is what the magnitude of the problem we're facing. And that's it. So thank you.
All right, thank you. We got a question? Was that what that hand was?
Yep.
All right, go for it. Let's get you a mic. Where's the question?
Hey, one thing I'd be curious about is, I know earlier we were talking about the bare multisig or the multisig stuff being stamps, which are going to be like unprunable. So I guess, or sorry, unspendable. But what I'd also be interested in some of your data points if maybe you delved in more into the degeneracy of the JPEGs and stuff, because I think there's a lot of address reuse with the inscriptions and stuff like that, and I'm actually really curious to know how much of that address reuse that you showed for, for your charts and stuff is actually people doing stuff with the NFT markets and stuff like that.
Yeah, there's definitely more to look at. This is kind of like the phase one. So we've planned out to do this preliminary analysis of the data and then look a bit deeper into questions like that. So how can we kind of categorize this, or can we qualify this a bit further? And what actors are doing what, and where is this reuse coming from? Try and put a finger on it a bit more. So yeah, it's definitely an open question and something we've got to look into further.
I could add a little bit more to that question, by the way. Just another thing I would point out is that most of the JPEG shenanigans happens in Taproot wallets. They use that to distinguish, like the Taproot address, the BIP86 derivation path. They like to keep the JPEGs in the Taproot address. So like it doesn't really matter necessarily whether you reuse that address or not, because the P2TR is potentially vulnerable.
Hi. So it looks like you've mostly focused on public keys that are publicly known to be exposed. But there are many protocols within Bitcoin and layers on top where public keys are shared with some parties. Like even within Lightning, you share public keys with your counterparties. There are wallets out there that share their XPub information with servers. Have you considered, have any opinion on what the amounts of those should be? Because it seems to me those are things that should be considered in this context too.
Yeah, that definitely warrants a further discussion. No, we haven't at this point. I think they're not public in the sense that everything else is public, right? So you've shared your XPub with Unchained, for example. Is Unchained going to then approach someone with a cryptographic quantum computer and say, hey, look what we got? There's some perverse incentives with that kind of setup. But no, that's further research to understand what that problem looks like. Yeah.
Next to you, Austin, left.
Thanks for the interesting numbers. Do you have also a number on the actual UTXO amount? Not the amounts, but the UTXOs. So how many UTXOs are in all those vulnerable addresses?
I do, but if you want to bring up the slides again. Like this. Yep.
Maybe you could read to us because we can't read that.
Okay, sorry if you can't read at the back. So block 900,000, we got paid to Taproot 600 million, paid to Witness pub key hash 45 million, paid to pub key hash about 50 million again, and Witness script and script 13, 2 and 13 respectively. So yeah, that was definitely, I guess the number is not about, it's less than 190 million at the moment. It's more like 168 or so, 170.
These are the types that exist in UTXO set today, not which of those paid to pubkey hash are reused.
Yeah.
Or am I misinterpreting?
Okay, so I haven't separated it out. That's not me, that's a Windows computer. I've got a Mac. I'm not sure if I've got it in here.
Okay,
I can
fine,
talk about it later.
Just one more question. You mentioned the address use for the top 1K addresses, and it's mostly like exchanges, and I obviously don't disagree that address use in general is bad. But I also think on the other side, it's a huge transparency increase if you have these public addresses from the exchanges. So, I mean, it's obviously not the best case of how you would do proof of reserve, but it's a case and people seem to trust it, and it gains trust in the exchange and stuff like that. Have you any opinions on how you would do that in a non-address reuse case?
Well, there's, I guess,
Sorry, could you say again what the supposed benefit is?
The supposed benefit is that if I want to like have if I have fiat in my bank account and now I have to make a decision which exchange do I go to, and you have like a bunch of exchanges that publish their proof of reserve for the last 3 years and it's all in that address, and I know they have like this big cold storage wallet, that gives me more trust to like why am I money to this exchange instead of something who doesn't publish anything. I mean, I'm not saying it's the best thing, but it's like a thing that people do today, and I'm wondering like if we don't have an address we use for cold storage wallets of exchanges, what would be a better way to do it?
Should I take the question?
I don't know, just
I mean, there are
Merch knows
bits about
everything.
proof of reserves. There's multiple methods that have been popularized over time that do not base their proof of reserve on address reuse. They generally are based on the output signing stuff. That's one of the big shaving points why the message signing hasn't been adopted for new output types, because people on the one hand are worried that it's going to be used by nation states to force Bitcoin users to show their funds, not just report how much. And but the message signing stuff works, it's implemented, and some exchanges very successfully have used that to prove to their own users or to their investors their reserves. I don't think that address reuse is actually relevant.
The signed message. I mean, doesn't just signing a message also leak the public key so it doesn't address the issue?
That's true.
So another point to that, and any kind of address-based transparency only shows one side, namely the on-chain holdings. It doesn't reveal anything about how much funds they claim towards their users. And a transparency report that doesn't have both is pointless. So I don't see the point.
Let's do, all right, we're at time. Let's continue this conversation. We have a big lunch planned later. For now, though, let's give another round of applause for Anthony. Matt Pines did such a great job earlier that we're bringing him back with Alex Pruden. Sorry, I saw your hand go up.
Hey, what's up, everybody? Quick intro for me. I'm Alex. I'm the CEO of Project 11, and I'm really excited to be here. I'm really optimistic and heartened to see this conversation. I was telling a few folks at dinner last night and this morning that I feel like 6 months ago, this issue was barely paid attention to, and now there's a really substantive dialogue happening, and very proud and happy to be a part of it, and we're very happy and proud to support this this event here today.
Well, I won't read my introduction, but just to kind of tee it off, right? So quantum threat model, that's our focus of discussion here. Just stepping back, like what is a threat model? Like why do you do a threat model? What are the elements of a threat model? So the discussion we're having today is about assessing the risk to Bitcoin from quantum computing. There's basic equation when you think about evaluating risk. You have threat times consequence, and you can decompose threat into threat actors that have the intent and capability to perform something that results in bad consequences. And so we're thinking about the mitigations to reduce risk. A lot of the conversations today and tomorrow are about technical mitigations to reduce the vulnerability of Bitcoin to a fault-tolerant quantum computer. The conversation we're going to have right now is, well, who might be in position the next few years along the technical development timeline that we talked about this morning that would have the intent and capability to have these bad consequences. And so we're going to talk more about that and kind of try to decompose that problem into maybe different component parts. But this is just sort of the conversation that we're going to maybe zoom out, right? So think about, there's no threat from quantum computing. There's threat from human beings that can use a quantum computer to attack Bitcoin. And so we want to say like, well, what's the threat model? It's not from a particular piece of technology. It's from a particular group of people using that technology to accomplish certain objectives. And those objectives, could maybe fall in 3 big buckets. They could be purely economic, meaning they want to get a financial payoff from the attack. It could be strategic. It's a nation state that wants to undermine infrastructure or cause a strategic harm to an adversary. Or it could be ideological. Maybe there's groups that just want to see cryptocurrency fail, and they want to demonstrate that it's a flawed technology. It might be other objectives, just people just want to inject chaos. But it's like zooming out, who are we thinking about modeling when we think about creating a threat model?
Yeah, and this talk is really going to be more game theory than deeply technical. And but I think obviously game theory is an inherent part of why Bitcoin works. And I think it's worth having this conversation because I think there have been a lot of implicit assumptions inside of several of these technical presentations that I think are just worth discussing whether or not they're relevant. And so, like, my background is in the military. And so when you plan an operation, you're always trying to red team it, as they say, right? So you're putting you're putting yourself in the position of the adversary, assuming you also have the adversary's goal. And what would you do? Like, what's kind of like the most likely thing to do, and what's the most dangerous thing to do, right? And so, anyway, kind of in the spirit of that, maybe we can jump in. So maybe maybe we'll start with a reverse interview question since I'm up here, but you were here.
Yeah, let's do it.
All right. I want maybe Matt. I think so. Maybe distinguish for us. I mean, given you've done some work in the government, and we've kind of talked about different threat actors and different categories of threat actors. Maybe start off with the nation state versus economically motivated, call them actors. I mean, how do you see that landscape with regard to a quantum threat to Bitcoin?
Yeah, I mean, we have to be. There's a theoretical component of this, but I think now we're at the stage where we can try to be as empirical as possible. I think the conversation we had this morning was very useful, right? We can list out the companies and nations that are going to be in position to conduct such an attack, and then we can sort of canvas that set of companies, academic organizations, and nation-state groups, and assess, which of them might have the intent to attack Bitcoin, and which will have the relevant capabilities. And I think if you do that kind of 2x2 matrix, I think you're going to sort of zero in on a pretty small number of candidate entities. And I think in that candidate set is probably going to be China and related entities associated with China. And so it's thinking about zooming in to the geopolitical context in which, say, China's entities, whether commercial groups that are state affiliated or outright sort of military entities, they might want to attack Bitcoin for strategic purposes, right? To discredit it as an idea, which is fundamentally threatening to authoritarian systems, as well as to undermine the United States if the United States continues along this path of kind of pro-Bitcoin policy. And so we see this convergence of the capability growing over time. We heard that this morning, and then we potentially see the intent of capable threat actors also growing as Bitcoin just becomes a more juicy target, and as the strategic motives to attack Bitcoin will also grow. And so that's just the context for any mitigation decision, is that a risk assessment is not a static thing, and a threat model is not a static thing. It's going to continue to evolve, and I think we see this acceleration in the technical capabilities and the acceleration in terms of the intent of different threat actors, particular, say, Chinese entities associated with the military, to leverage these breakthroughs in order to accomplish a particular objective. I think there's questions about commercial motives, right? Folks at the frontier that may have the capability to attack Bitcoin, but there's a large matrix of norms and laws, fiduciary obligations, internal politics that act as constraints for maybe the first mover technically from being the first attacker, right? And that's not to say you would eliminate those from your threat matrix, but it means that there's going to be other mechanisms potentially that would constrain those entities that might have the capability to attack Bitcoin from being the first ones you should worry about, right? And there might be fast followers that have the intent, and as soon as they get close, they might try to hit it. And so this is the combination of modeling not just who's at the frontier technically, but who has the set of political objectives or strategic objectives or economic objectives or all three, that as soon as you get to that threshold, that's the alarm.
Yeah, and I think I want to emphasize a point here that's kind of been implied several times, but to make it kind of explicit, which I think is important, that this is a non-attributional attack, right? Like, it doesn't necessarily have to reveal you as a quantum attacker, right? So we talk about costs to the adversary, right, for, let's say, a nation state, like China, the PRC, right? There's obviously the cost associated with building a machine that's capable of doing this. But one cost that is not a factor in pulling off this attack is potentially reputational risk or political risk, right? Because you can just call it 100 other things. What's the difference between losing a private key and someone stealing your private key with a quantum computer? That's a pop quiz, and the answer is there is none, right? Like, it's just, you're just going to have, someone else will now have the private key. So I think that aspect of it should really be considered. And I think, by the way, that extends all the way over into what we'll call, an economic adversary, which is just a broad class of people that potentially just want to profit from the fact that they have a machine that could recover Bitcoin that is worth something. And I think in either of these cases, I think it's very important to emphasize that if you're clever and your goal is to continue operating, continue to use this system that you've probably invested quite a bit in building, you really have absolutely no incentive at all to, let's say, go after Satoshi's coins, right? Now, I think there's probably some edge cases where, like, if you're China, potentially you want to kind of introduce uncertainty and maybe that's your goal. But certainly, I think from an economic perspective, you have absolutely no incentive to reveal this. And, for other applications of quantum cryptanalysis, I mean, this is also true, right? So if China had a quantum computer and they wanted to read the NSA's emails, it doesn't really do them any good to publish that fact at all, right? And so kind of zooming in on I think another point that I want to make is that in rewinding a little bit earlier this morning to some of the things, hey, like what's the timeline? How are we going to mitigate this? I think it's very important for all of us to recognize that there is no guarantee that you will see this coming from very far away, right? Now, obviously, that, again, most likely scenario, most dangerous scenario. I'm not saying that this is all going to happen in secret. I think Terry did a good job of dispelling this myth that, like, the NSA secretly has some effort. But bottom line is, I think things could happen quickly, and I think beyond a certain point, there is not, from a game theory perspective, you don't have an incentive to reveal your capabilities as the adversary. So,
Yeah, I think there's maybe two canonical scenarios to worry about. There's probably variations, but there's a sort of there's a blitz attack where someone has this breakthrough. Maybe they've been doing this sort of secret application of their breakthrough capabilities, and then all at once, coins just start moving, and then it's panic and it's bad news. And then there's a slow bleed where they sort of pick off high value UTXOs over time, but it's ambiguous, right? We saw the movements last week. There's not going to be like a quantum canary that actually says I'm a quantum attack, right? And so we're just going to have this constant debate, up until the point where it's obvious that something nefarious is happening. But you have to model like, well, what is the threat actor trying to achieve? If they just want to sort of peel off for like really valuable coins, well, they're probably going to do it very covertly. If they actually want to undermine confidence in the entire network, or they want to have a massive strategic impact, well, then they want to hit it all at once. And so you're talking about like, what scenarios are you planning for? Well, what sorts of threat actors are you trying to model? And what's the worst case scenario? What's the most plausible scenario? And what is going to affect the timeline associated with any mitigation or response? The last point is we talk about technical vulnerability and in terms of actual movements of coins as being one of the alarms that we want to, that we expect to trip. But we exist in a mimetic economy where even last week when those coins are moving, it was the question, could it be quantum? And I think because the baseline expectation is that quantum computing is not a material threat, that I think the default reaction is no, right? But as we progress along this technical roadmap in the next few years, anytime you see coins like that move, I think the changing distribution of priors is going to make that question more a live one. And all that it takes for have a market movement that is potentially unstable is just the threat perception. Whether you actually have coins move or not, if people perceive that the threat is rising, it could be a nonlinear kind of social response. And so one scenario that I think about is, imagine in 2 or 3 years, there's an op-ed written by David Ignatius or some similar kind of, deep state journalist, and he writes an article saying that multiple sources indicate to him that the U.S. intelligence community strongly suspects that China has achieved a breakthrough in quantum computing, and that they have been decrypting secret U.S. government information. So that article gets released. There's no proof. There's no obvious indicator whether it's true or not. What do we expect to happen, right? Do we expect that to just kind of be washed, be sort of in the news cycle? I think the priming that is being that is happening in the community means that will trigger immediate urgent discussions. Well, how far are they along? Does this actually pose an immediate threat? And this is going to bring lots of other people into the conversation that aren't in this room, right? It's going to bring in large custodians. It's going to bring in large, it's going to bring in financial regulators. It's going to bring in other countries. And so the conversation about what to do and when and how is going to vastly subsume, I think, the conversation we're having today. And so just like modeling in not just the technical threat, but like the psychological threat associated with the perception changing over time.
Yeah, and I think another piece of that is, and connecting back to an earlier point that was brought up in the like quantum computers and their differences, right? What is a cryptographically relevant quantum computer? What is relevance, right? And I think relevance is highly context dependent, right? And I think this is maybe a myth that I'd like to just take the opportunity to dispel. I think a lot of people, when I bring this up to them, they're like, if a cryptographically relevant quantum computer came online, we're all screwed, like the world falls apart. It's like people used to talk about Y2K. I don't know if anyone remembers Y2K. It's like the world is just going to explode or whatever, right? But the reality is, from like a cybersecurity perspective, attacking financial infrastructure, not Bitcoin, comes with a lot of associated challenges, right? So like, unlike Bitcoin, right, your bank account is not assets in your bank account are not bearer assets. Like there is an institution that are holding them on your behalf that you authorize to send for you, right? And there are kind of a lot of layers between the sending of that money and you requesting. And it's not very straightforward to target that. In fact, even if you did want to, like kind of the most obvious way here is like, you have a TLS session potentially between you and your bank that you could man in the middle, but like, how long are these keys for that specific TLS session really vulnerable? The reality is they're not that, these things are not that long-lived, as opposed to Bitcoin, where these keys, as we just saw in the last presentation, there is a significant number of keys that we all know, we can all see, and by the way, it's like a giant billboard in the sky, like this is exactly how much money there is associated with this exact address, and by the way, like, maybe you don't need Terry's photonic computer. Maybe you've got the vacuum tube version of this with some cold atom thing. And yeah, it takes 200 days to run once, but that honestly is probably fine. And it may not work for any other context at all, but it would work for this. And by the way, just if you multiply the current price of Bitcoin, which I don't know off the top of my head, times the vulnerable addresses, you could probably just fund an entire effort just around that with your quantum computer that does nothing else. And so, again, these are just, this is not like a pronouncement of what will happen here, because I can't see the future, obviously. But I'm just trying, and Matt and I are just trying to expand kind of all of your minds and just think through all these possible other ways in which this threat might manifest that we potentially haven't accounted for up to this point.
Well, and there's a critical feature of, think about that equation, like risk equals intent times capability times, consequence, right? And think about mitigation measures or different, ways that you could try to reduce the threat actor's intent, reduce their capability, maybe that's a little bit more difficult, or reduce the vulnerability, right? And there's a reflexivity and interdependency between those different things. So if you meaning broadly, the Bitcoin community can credibly commit to a feasible mitigation strategy that the attacker believes is credible, that might reduce their incentives to actually undertake that attack. And so I think in terms of different scenarios for how this could go, right, over a rough timeline. There's like the worst case scenario where there are actual secret groups that are ahead of the curve publicly, and they decide to undertake a catastrophic attack. So that's like a bolt from the blue, sort of blitz attack. And say that happens instead of the 5-year horizon, say it's 3 to 4 years. That's like worst case scenario. We're caught by surprise, and it's like absolute break glass. What do we do? And then there's a scenario where maybe it's the central point of the sort of estimates of 5-6 years where we get to a fault-tolerant quantum computer, but maybe the first people to get there aren't the bad actors, right? So we get a bit of a heads up. This is coming, but now we know that maybe the bad actors aren't far behind, right? So it's like, we now have a clock. We have a year or two before we think that the bad actors might actually get to the breakthroughs that the good guys have gotten to. And so now we have a bit more urgency. We don't have like a catastrophic sort of surprise, but now there's like a very clear 1, 2, 3 years maybe to like actually accelerate to a quantum safe state. And that's gonna be a risky scenario. That's like, do we do it in time? Do we actually get the community to understand what's actually happening? Can we actually communicate this effectively? There's a third, maybe the more optimal scenario where the technical roadmaps are a bit optimistic. We have a bit more time than we thought. but the community actually takes it very seriously. And we get everyone on board, and most of these addresses that we saw that can move, do move, and effectively you've mitigated most of the potential risk. There's still obviously that large hanging chad of potentially 2 million coins you have to figure out philosophically what to do with. But from like a actual kind of preparedness and mitigation planning, you have the time. And this is ideally the scenario that we'd be in. The fourth scenario is like the best case. This is all hype. There's actually nothing to worry about. We do all this for nothing. We move all the
Sorry,
coins.
Terry.
We have there's some sunk cost, right? We spent spent 2 days talking about this for no reason. But we had some fun. And or it's like 5 or 10 years even further away. That's like, maybe the best case scenario. I'm not sure that would be the baseline to plan on. So thinking of in terms of the distribution of those scenarios, you have to sort of build into your model the technical roadmaps. You put a discount factor, maybe some commercial hype or exaggeration, but I don't think they're going to be too wrong. And then the threat actors that could be close behind them, that as soon as they get it, the incentives either economically or strategically are going to be much higher than they even are today. And so I think if you just do a discounted, expected value, right? If there's trillions of dollars of potential loss in the future, and you have, maybe even a 5 or 10% probability assigned to that loss function, that's a huge present value risk that it would be rational to mitigate.
Yeah, and so we'll probably maybe conclude here and let some other folks just weigh in. I mean, I would say questions, but ultimately, like, this is game theory, this is wargaming, so this is opinions are as welcome as questions. But just reacting to what you said, I mean, all these estimates are clouded by uncertainty, right? So we don't actually have really high fidelity estimates over, for example, like how far behind is the malicious adversary versus just someone who wants to quantum compute for good. We don't really know, right? Then you're not going to know. But what we do know is there's a lot of people with hair triggers in the markets, right? Because people are very sensitive to these things. And this maybe gets to the last point around, since we're threat modeling. I'm very proud and happy to be part of the group in this room. But the group in this room, I don't necessarily think is entirely representative of every Bitcoin holder. In fact, if anything, I think this skews very heavily towards a specific subset of people in Bitcoin. I see a lot of faces around here who've been instrumental to even getting to this point. And I think increasingly in the past couple of years, we've seen more and more economic actors getting into the game, and it's not 100% clear that I think the values that we implicitly hold together in this room are universally held. And I think the risk here, the threat here, is that this comes faster than we expect. We don't have time to come to consensus, but money talks. Like, there's a lot of money to be lost or gained, and there may be compromises that some Bitcoin holders, I don't think anyone in this room, but some would happily make to preserve their financial wealth effectively. And by the way, some of this may be entirely forgivable because some of these are institutions with fiduciary duties, right? And so I think going back to like the happy path here, I mean, again, like this is step one here. We can start, planning and laying the groundwork now and ultimately hopefully reduce the threat by doing so. So maybe that's a good spot for us to end, and maybe we can, Austin, take people who want to chime in.
D++.
By your estimation, and maybe you haven't thought about this or studied this, but is there some amount of capital that would like to flow into Bitcoin, but is either waiting to or is hesitant to because they're concerned about this looming quantum threat?
Yeah, I mean, I'll ask Alex Thorne. He probably has this conversation, but I think it's significant.
Like trillions, or I mean, it's hard to quantify.
I mean, my understanding, and I've had these conversations not just with the folks. Again, like the political economy of this is important to model, right? There is Bitcoiners, and then there's a subset of that are the technical development community, many of whom are in this room, and their priority in their assessing risk is the core function of the protocol, the ethos of the protocol. That's how they kind of do the risk assessment. There are now other entities that have large equities in Bitcoin that have a different set of priorities, right? So there's the major custodians, the ETFs, the hedge funds, the BlackRocks, and they look at just as a purely financial sort of risk calculus. And so BlackRock put quantum into the risk disclosures, and I'm sure they're doing modeling of what's the downside if there is a successful quantum attack. And so they're having these conversations with other investors. And so this is now part of that risk calculation of, well, okay, this is the last thing that I need to see mitigated, credibly, before I'm going to push my allocation from, say, 1% to like 10%. I suspect that's happening. I don't know how to put a number on it. Go ahead. Yeah.
BlackRock, and I can absolutely confirm that they've done a ton of market data on this. They're extremely concerned. Also, something we can confirm is that governments, we've been approached, Marathon's been approached by folks who work at various different levels of government who are basically saying that they are deciding how exposed at the government level they want to be to Bitcoin in terms of how much Bitcoin governments will acquire, things like this, based on our plan, in quotes, as a community and how we're going to be, handling this potential threat, which is really fun to try to explain to them how Bitcoin governance works. So yeah, I would say both of those things are definitely happening.
Yes, and it presents maybe a separate conversation we can have, which is, I come from a cyber world where, say, there's a nation state that's has a zero-day exploit and they're rampaging through some critical infrastructure networks. There's a procedure the government has to bring down what could be very highly classified threat information and share it with the private sector. And they have a whole set of infrastructure, ISACs, to do that kind of terror lining, sharing it with the private sector. And so that's how the US government works, is they need to find somebody to share that threat information to. To that exact point, if someone in the US government goes, oh, we have a classified threat assessment of, say, China's quantum computing capabilities, and maybe we have intel that they want to go after Bitcoin. Well, who are they going to share that with? There's no Bitcoin CISO, right? There's no one to be like, yeah, I'll take that information and I'll be the one to credibly execute a plan. The U.S. government doesn't have the sort of mechanisms to understand how to engage with this kind of decentralized. I mean, I don't know. Well, then who do I talk to, right? I'll spew it to the mailing list. Yeah.
We got Ava over here, and then I know Jesse probably have time for maybe 2 questions.
So since this topic is threat modeling, I'm wondering, was there any what considerations do we have from the completely other direction? What if, and this is very cynical, what if this is all just a massive psyop for us to implement a quote-unquote post-quantum algorithm that actually just has a huge backdoor for someone to exploit? Because this is...
Yeah.
This is also a possibility.
I mean, I think there's even a slightly kind of less cynical or extreme version of that, whereas this is all new cryptography. Implementing these things is hard, and in the best of times. And I mean, even if there is a legitimate quantum threat, that may actually even be the lesser of the 2 evils than introducing some significant vulnerability that lets people classically steal funds. So, look, I think that's, again, I think this gets back to I think there's a danger to believing too much in the optimistic timeline, because I think we have to think like we're in the worst case scenario to ultimately prevent the worst case scenario. Going back to Matt's earlier comment.
Yeah, I mean, it has to be a scenario, right? The NSA has introduced backdoors into publicly known crypto. It's their SOP. So these NIST schemes, right? You have to understand that the NSA approved them. And the NSA likes to ensure that they have, access to things. But they're also rolling those same schemes out to the entire federal government. So there's a bit of the way the U.S. government does crypto policy is very complicated. I think it's changed over the years, and that risk-reward calculation associated with introducing backdoors has changed since the Snowden leaks. So I don't think you can eliminate it, but it's smaller than I think it has been in the past. And so it's a perception of the threat, and maybe that's why you need to have crypto agility. You need to ensure you're not relying on just one post-quantum scheme, but you have multiple, and then you have the ability to swap others in. So if you find some holes or some weaknesses in one of these schemes, you're not totally relying on it.
I think we're at time. Thanks, guys. I'm sorry, there's a ton of questions. We'll be around. So,
all right,
yeah,
there
thanks.
we go. Let's give it up for Matt and Alex. Round of applause. Our next speaker needs no introduction, but I will give a brief one anyway. Lalu. One of the things we've spoken about today is there's different post-quantum signature schemes. They rely on different mathematical assumptions. A lot of things that I'm not qualified to talk about, which is why we have Lalu here to talk about some of that.
Hello? Hey.
All right, so as mentioned, so like I'm interested in sort of like more of the concrete, things, and sort of like I think there's definitely like a big philosophical argument on sort of like what happens, how do we coordinate. I'm more interested in sort of like what are the schemes, how can we do it on Bitcoin, what constraints are we worried about, and in particular, exactly what parameters can we have that maybe tune something a little more towards Bitcoin, right? So I'm going to focus purely on hash-based signatures here, and I'll give you a little sort of like overview. And so I think it's relevant to sort of like give more motivation of like why hash-based itself, right? So obviously, as we know, ECC and RSA they're going to be broken by this stuff, and scaling it up doesn't necessarily seem feasible. There are lattice-based schemes that we talked about a little bit earlier. I mean, so I would say the advantage of these schemes are like they have more structure, for example, so you can probably do things similar to what we do in Bitcoin around like key aggregation, these different type of proofs and things like that as well too. But they have like newer assumptions basically, and also there's also some implementation pitfalls as far as like properly sampling the distribution. You basically need to restart a signature sometimes if it actually doesn't work with a certain probability, and I think it's a bit more hairy than some of the hash-based schemes. There's also a code base as well. Codes base like have like very large public keys. To my knowledge, they actually haven't been standardized by NIST as well too, right? So I think hash-based is basically the way to go, right? And the main thing is that if you think about it, every single signature scheme has a hash function in it already at some point, basically, right? So you're not necessarily adding any new assumptions to it itself, right? And also, Bitcoin already uses hash functions everywhere. We have the Merkle trees, we have the SIG hash flags, we have the TXIDs, we have all that stuff as well too, right? And if you look at the security proofs, they are reduced down to basically some property of hash functions, right? Either maybe that's collision resistance, second preimage resistance, and so forth, right? So these are things that we already know, fairly well. And also, one thing is after the NIST SHA-3 competition, I think cryptologists say basically have a very good idea of how security of hash functions actually functions basically in order to actually reason about these things effectively. The signing and also verification is fairly fast because once again it's just hash functions. There's no asymmetric operations or as far as cryptography itself. And most laptops, phones also have like SHA-NI basically, sort of like an optimized hardware accelerated version of SHA opcodes basically. And also there's different things you can do as far as vectorization to hash a bunch of values all together, right? And some of these hash-based schemes are very much optimized for hash functions in terms of doing things like reducing the compression function instances. Maybe that means some pattern with SHA-2, and SHA-3 is a little bit different as well too. And one big thing of Sphinx Plus is actually it's fully stateless, right? So one thing with some of the other hash-based schemes, maybe it's a one-time use. Basically, you need to maybe remember exactly like which keys you used in the past. The way Sphinx works, it's a massive tree as we get into a little bit, and the idea is that basically you can just keep using these signatures because the tree is so massive you'll never run into a collision, right? That's sort of like intuition about it, right? So as I was saying before, I think it's suitable for Bitcoin because we have Merkle trees everywhere. We have SHA-2. It actually also uses SHA-5 in some of the constructions, just because sometimes you basically need a slightly larger output size, but not too different basically. And the big thing here is like there's not necessarily any entirely new cryptographic primitives introduced, right? You are constructing sort of by via composition, sort of like what we already know and use today, in Bitcoin itself. But there's no new scheme around like maybe a hardness problem that doesn't reduce down something that we already know today with as far as hash functions, right? And so I'll give you a little intuition on the way that things work. So there's sort of like a few time and a one-time signature scheme, right? One-time signature schemes, or maybe you've heard of something like line 4 signatures, basically, where you sort of like have these pair of hashes, you hash it up, and you basically reveal a hash based on the bit itself, right? That's a one-time signature scheme, right? So the way that Sphinx works is basically it takes a few time signature scheme, something that you can use a few times and sort of like have degraded security. It signs a message with that basically, and it has like a massive tree of one-time signature scheme public keys basically, right? And then as you go up the tree, you basically sign the one-time key public key with the root of the lower layer basically, and you keep bubbling up from there itself, right? And one interesting thing about it, I'll get into it a little bit later, is that like it actually natively supports sort of like public key recovery as we know in Bitcoin, right? Because the validation algorithm is basically you have these Merkle proofs basically that are revealed, and you're checking that the hash of that root thing basically matches the public key already, right? So you can save a little bit of space, but the public keys are actually fairly small. They can be 32 or 64 bytes, similar to what we know today with elliptic curve cryptography, right? And here's sort of like a scheme of it, right? It's like, hey, yo, dog, I heard you like Merkle trees, so we put a Merkle tree in your Merkle tree so you can Merkle while you Merkle, right? And so this is the way it works right here. Like, so you start at the very bottom, right? So you sign the message with a for scheme, right? And basically the way this works is that like everything is somewhat deterministic. You have a seed, and from that seed, you can basically derive all of these various indexes, right? And you can basically, view this, tree as a way you can basically address it. You're sort of like viewing the Merkle tree or the binary tree itself as sort of like an array. You can basically have indexes into that array that represent the actual tree. It works. That's the way it goes. And I'll get into this a little bit later, but like there's a few parameters that once again control sort of like the signature speed and also the size of the signature itself. And I think this is an interesting thing around sort of like picking some of these parameters with the way they work with Bitcoin, right? One other thing is that like so with this scheme, like typically the NIST scheme, like it's good up to like 2 to the 64 signatures, which is like a massive amount of signatures basically, right? And in practice, you don't necessarily need that many signatures. So like once again, like just for use, so we say maybe someone's reusing something thousands of times basically. The parameters we can say, okay, well you can use it 20 million times or 1 million times, which is actually pretty good, right? And probably the only scheme that we have today that's widely used that like generates a ton of signatures with the exact same key is Lightning channels, right? Maybe very, very old Lightning channels, maybe they sign with the same key millions of times, but for the most part, like a normal user like is going to sign maybe 10, 20, 30, maybe an exchange, millions of times, but not necessarily billions, trillions, because 2 to the 4 is a very, very large number, right? And then so you start with the message basically, you sign that with the for scheme at the very bottom, and then you're basically going to go up progressively, and then sign the root of the the signature of the for scheme. We'll get into what that is later with a one-time signature scheme, basically, right? And then that has another layer, which is a series of one-time signature public keys, right? You make a tree from that itself, and then you sign the root of that. Right? So basically, the way a signature works, you basically start at the bottom to verify it. You verify the signature for this one, and then you're just doing Merkle tree inclusion proofs all the way up, along with one-time signature checks until you get to the root. After you get to the root, then you sign it, right? And this is going to come in a little bit important because we can play with these parameters. For example, D, the total number of Merkle trees; H, the height of the Merkle tree; W, the winter width parameter, which basically is sort of like the length of the hash change versus how many actually hashes you have, and then things with the fours as well too. And so, let's go into winter nits. This is one of those things where it's like I've said it a bunch of times in my head, and I realized I was saying it wrong. So it's winter nits. I always said winter wits for many, many years until someone said it out loud. Like I was like, okay, winter nit signatures, right? So basically, the way this works, you have like a series of secret key values you generate randomly, right? And so what you do, you basically have a message, and that message basically tells you which secret key values you're going to hash like n number of times, right? So the public key just starts with the secret key values. Sorry, the secret key is just the values. The public key basically hashes all of those n times. People have seen things like atomic encryption, basically, where typically they have something where you hash n times. There's different forms of some sort of like proof of space and time kind of thing, which typically involves some sort of like trade-off for that. This is effectively that, right? So the public key is then like you basically take all of these these end hash chains and then make a single hash from that using tweakable hash digest. And here's a great diagram by Contuition from Twitter, maybe just in his blog post, of sort of like how this works, right? So at the bottom you have like your secret values. You then hash those n times, and then based on the message, there's like a checksum and some other details as well. You basically know how many times to hash any of these like secret links, right? So basically the proof is basically like a hash link list, right? And that's sort of like the way the one-time signature scheme works. Then we have fors, which is called forest of random subsets, right? So there's two parameters that's associated with this, k and a. So k is the number of trees, basically. Once again, it's all just Merkle trees, and then a is basically the height of each Merkle tree. And then similar to the one-time signature scheme, watts, you basically take some sort of like digest, and then from that figure out exactly number one which trees to reveal, basically, because once again you reveal from a subset of trees, and also the leaf in each tree to reveal. And here's another great diagram by Contuition that basically shows how this works. So at the bottom, once again, you have these secret values. You hash those secret values. There's these, n or k trees, basically. The public key is the hash of all the actual trees. So you basically have the message digest and the indexes, and you're going to pick, okay, I'm going to reveal this leaf, and then that, and self. And then once again, everyone can just validate it works, because validating a signature is correct means that, okay, well, these Merkle tree inclusion proofs give me the exact same public key, and that's the way the for scheme works. And then this is the next thing. So it's cool because Sphinx, like, initially it seems very like unwieldy, but like once you understand each of the individual schemes, you're basically just composing those schemes into one final signature scheme, right? And the final one is the XMSS, which is basically sort of extended Merkle signature scheme, which is actually a super old signature scheme, made by Ralph Merkle back in the day. Then people sort of like improved it a bunch, right? So this is the portion of the hybrid tree, right? So what we do here, we have, once again, a bunch of one-time signature schemes. We make a Merkle tree from that itself, and then signing this thing is basically revealing one of those leaves with a one-time signature scheme as well. And I say what's plus here because if you get into it, there's like different versions of Watts. Some of them basically, ended up modifying the checksum, adding another XOR value. The way the Sphinx paper did it, they basically have something they call like a tweakable hash function that sort of like takes place of the XOR and make things a little bit smaller, and they just hash all the keys at the very end, right? And then we have the hybrid tree, right? So ideally, you can go back in the slides later. I'll publish them. Now you can basically understand exactly how this works, right? It's interesting because like the public key is generated, or rather like all this is fairly deterministic, right? So there's like a secret private key, and then from that you're able to generate any of the preimages as far as like the watts, the forwards, whatever else. And then in order to generate this, the public key, you basically just generate only the top layer of the hybrid tree, and then hash that, and that's your public key that you can put out there basically. And I was saying, so like this multi-layer design is actually some of the improvements. There's actually something called Sphinx. This is Sphinx Plus, and there was some prior versions of that, and this is actually what makes things feasible and effectively stateless, right? Like it's stateless in that the number is so big that the collision probability that you actually get the exact same, instance basically for a different message is fairly low basically. So that's like the hybrid tree structure, and hopefully now you guys know how hybrid trees work. But yeah, so this is I mentioned a little earlier about signing and verification. So signing basically starts at the bottom. You basically do the forest pair. You go all the way up. You're basically signing every single layer of the hypertree root, which is a Watts pair. You have the final signature. The verification basically works a similar way. You basically have this massive proof as a serialized proof. You start at the bottom. You basically verify matches the public key, and the public key doesn't necessarily need to be in the script. Maybe it was in the output script, as we'll talk about later. And you basically just verify that everything hashes, and it's all good. And so this is probably one of the main things that I was monitoring the NIST PQ forum basically, and there's this paper that I think I'd read a while back, but they reached out to individuals because, as you see a little bit later, some of the parameters that NIST recommended resulted in fairly large signatures that were somewhat slow to validate basically, right? And that's because they were going for the ultimate level of 2 to 64 signatures, right? But in practice, people don't necessarily need to generate that many signatures. I definitely encourage people to check out both the forum post and also the paper itself because, for example, there was a bunch of people from maybe their rent certificate authorities. They're okay, well, even if we have 100 concurrent signers and we're signing one message every second or whatever else, it's going to take us a million years to actually go to that parameter, right? So it's cool because a bunch of people from the hardware industry, maybe they're signing some hardware key, maybe they're doing some validation, the certificate industry, whatever else. They kind of okay, well, we don't necessarily need those super duper conservative parameters. Maybe some things will still use that, but we can once again play with these parameters in order to do things that I mentioned before. Hashes are fast. There's no sort of asymmetric operations, and you can do a bunch of hashes a second even on your laptop itself. Next slide. So these are the official NIST parameter sets, right? So it's divided into one. There's sort of SHA-2 versus SHA-3 or shake basically, and also they divided into the number of the amount of security bits you get. The bits of security 128, 192, and 256, right? And as you see, even the smallest one is around 8 kilobytes, which is fairly large basically, right? And the nice thing for all of this is either way the public key size and the secret key size are fairly small. For example, if you look at something like the code base, you have hundreds of kilobytes of public key size. This is pretty nice because once again, you can just put this thing, and also the public key is already a hash, right? So you don't need to also do another hash, which is some page script hash that some of us know are fairly well, right? So this is what they went at. They're saying, okay, well, these are the super conservative parameters. These are fairly large. For example, a 50 kilobyte key, and people are thinking about things like TLS. Maybe it's something that attests to a BIOS or some other bootloader or something like that. They want these things to be fairly small. And also, once you get into the hardware environment, imagine your hardware wallet generating a 50 kilobyte signature, right? That's a lot. And typically they're fairly limited in terms of memory and what they're doing as well. So can we get this smaller? And the answer is yes. So this is a super interesting paper because it looks at a few things, right? So one thing, because we have this massive hypertree, you're generating a lot of hashes, right? And so they were saying, okay, well, what if we set a budget of 100,000 hashes, 1 million hashes, 10 million hashes, 100 million hashes, 600 million hashes, right? It sounds like a lot, but with SHA-NI, you can generate hashes, just in terms of nanoseconds, basically. You can also even, use vectorized instructions, basically pipeline this stuff and get it down, pretty slow, right? So using some of these parameters, we can actually get signatures down to around 3 kilobytes, right? So you can do this lower as well. So for example, this is looking at the number of allowed signatures of 2 to the 20, which is roughly a million or so. You can go smaller than that if you actually wanted to. If you go even smaller, you can get this down to 1 or 2 kilobytes, right? And maybe you'd go smaller. Maybe you wouldn't use that for Lightning channel. Maybe you'd use that for a normal spending wallet that doesn't necessarily do very, very high throughput, right? And so the signing cost is interesting there because number of hashes. They typically do number of hashes because they're looking at the sort of asymptotics in this case, and it depends on your implementation, right? The hardware, exactly what you're doing, your optimizations, and so forth, right? And one interesting parameter they have here is what they call overuse safety, right? So overuse safety is the number of signatures that you can safely generate beyond the number of allowed signatures, and then degrade to a lower, number of bits of security, right? So I think it was 128 goes to 112 bits of security, maybe I think it was 256 goes to 192, and then so forth, right? So this is interesting because you can play with these parameters, and the overuse safety is sort of your budget of messing up, right? For whatever reason, if the user messes up and they have a while loop running, or they have some other scheme, or there's some Oracle attack in some protocol or something like that, this is what you can tune, right? And the main thing is that you as you sort of increase overuse safety, you end up generating more hashes, and as you'll see later, the hash is based on the height of the hypertree. Oh, good.
Would that be for the same public key?
Yeah.
So actual address reuse of more than 205 times 1 billion.
Yes.
And only then security goes down on the same.
Yes. And it
script.
doesn't break immediately. Basically, the way the modeling, it starts to degrade over time. And if you look at the paper, there's a bunch of cool graphs around sort of as you do more and more hashes, how much what your security level degradation actually is. So it's nice because it's not something like on short signatures where if you reuse the nonce, again, boom, your hose basically. This is sort of something that actually degrades, over time. And the main thing you can look at is also verification. So you can see the number of hashes to sign is much larger than verification because one whenever you're signing, you're actually generating all of these intermediate trees depending on the hypertree construction, and also you're doing more hashes. If you look at something like Winterwitz, maybe you're going to hash it halfway, and then they do it the other way, or 3/4, and then so forth, basically. And you can get that down as well. And this is still like fairly fast because 450 hashes are still super fast. If you look at things like cryptography, even with all the optimizations, you're just generating a hash. And like in order to generate, like let's say you're making a SIG hash of like a fairly large Bitcoin transaction, you may generate hundreds of hashes in the process, right? So it's not that different in that case. And then so this is important because this is about the sort of like the level of parameters and like what you can do for each parameter to tweak exactly the size and the how long it takes to generate a signature itself, right? So first you have H and D. So H is the total hypertree size, right? And then D is the number of layers in each hypertree. So the thing is, if you increase D, you have to also generate more Winterwitz one-time signatures, or the WAS signatures basically, which increases the size of it, right? But if you lower D, that means you need to generate the entire hypertree potentially all at once, which increases the signing cost and actually increases the number of hashes as well. Similarly, we have K and A for fours, right? So K is the number of trees, and then A is the height of each tree. So once again, if you reduce the number of trees, but increase the height of the tree because you're still going for that same level of security, you may have bigger signatures. And then finally, W is the Watts parameter, which basically states sort of like how large the word size is basically, which determines how many hashes you actually have to generate and the number of hashes as well. So you can play with all of these and actually have like a really cool code base basically, lets you plug in these parameters and do some simulations on them, and that's how they arrived at the ones that they ended up putting in the paper. And these are just some of the ones that I chose. So for example, they also go to 2 to the 30 and 2 to the 40 allowed signatures. They also, and this is level 1 security, which is 128-bit. There's also level 3 security, which is 256-bit as well. I think the smallest one for that was like 7 or 6K, so I ended up leaving it off. But like, there's actually some liberty with these parameters here. Yeah, and then so that gets me into okay, what about Bitcoin? Like, how does it actually work on Bitcoin, right? So I started looking to this stuff. I have some code that's not fully ready yet, but hopefully I publish it in the next few weeks. So let's say we have like a hypothetical, op, SLH, DSA, check sig. We can have a better name, Sphinx check or something like that itself. So one initial, issue is that TapperScript actually has a 520 byte stack limit, element limit for each element of the stack, basically, right? So for example, this is nice because this means something like a opcat can't just like explode the size because you actually have that restriction there, basically. So maybe there needs to be some difference there. For example, maybe we can actually put the signature in the annex itself, which isn't necessarily subject to any of those issues. And maybe the check check operation actually reads the signature from the annex and then validates like that. That's one example. As I was mentioning, like the small signatures, it can be around 3 kilobytes. One of the things that you also need to figure out some sort of like analog with SIGOP cost, right? So people that don't know with the way TapperScript works, every single signature is basically 50 cost, right? And there's a total limit for within the block itself, right? Once you go below that, then you basically have an issue as far as SIGOP cost. So this means, like, for example, there's only so many signatures you can have for multi-sig and then so forth, but obviously things like MuSig2 help with that. So one question is, okay, well, we're generating a lot of hashes, right? As you see here, like, potentially, millions of hashes, but like, once again, that's just signing. Verification isn't too bad. So I haven't, run this yet, but it seems similar to, like, if you have some, like, massive transaction, how many hashes are you generating if it has, like, 1,000 inputs or 10,000 inputs or so forth, right? So the question is, like, do we actually need another, I think I jumped ahead a little bit. Yeah, do we actually need another like costing mechanism, or is the weight of the block already enough? Maybe it's not, because once again, these signatures will still be 3 kilobytes or so, right? So you're not necessarily going to like DOS someone by making them do a bunch of stuff, because they're just hashing, and it's a little bit cheaper than signatures, and you can also do some of this stuff in parallel as well. And then so I was thinking, okay, like, let's say you wanted to go away from sort of like the current TapperScript version. I know people have different ideas. So, one idea basically you would have like your normal script root, basically, like let's call this output hash itself. But then you would also have the key spend key hash along with that, right? Which still lets you do sort of like a smaller reveal for the key spend case, and then still have the script path as well, right? So it's slightly different because the way Tapper works, above, we're actually leveraging some of the properties of the structure from elliptic curve cryptography to let you basically do this like tweaked output key and then reveal it and so forth. But it's okay. Well, maybe we're not necessarily going to have that like EC aspect of itself, but we can still sort of replicate the cheap path for key spend and then the expensive path for actually doing the hashes there. You can get into it. Maybe you can increase size of the hashes because, for example, I think it's like you have like an n/3 reduction on the hash size. So 256 would need to be 384 and then so forth. But maybe that's not really an issue because you still have preimage resistance, second preimage, and so forth in that itself. So one other thing, along with this is that like because now we're basically just in hash line, and hashes like don't have any structure, which is also nice because there's no structure, there's not as much room for sort of like more clever ideas around like, oh, if I manipulate this algorithm, I can do this and blah blah blah, which is typically how some of these speedups work or in terms of breakages. So you can't actually do public key derivation the way you can do with BIP32, right? Because BIP32 it exploits all of these different properties of I have the public key, I can derive a public key that they can have the private key to without them knowing, and there's some different things about that. So it seems like you would actually lose that that going in the hash-based direction itself, you can still maintain deterministic, seed generation basically, but you just can't have that public derivation itself, right? So this may change the way some wallets work basically because now they just need the key itself. Once again, it's nice because the key is just 32 bytes. It's not massive like some of these other, schemes itself. And watch-only wallets would need to be a little different as well. But once again, like you could give them like a, once again, another Merkle tree, a Merkle tree of all of your public keys basically generated from this itself. You can give them proofs basically to like, authenticate those. So that's like one thing when investigating this stuff, something that is a little bit different today. And this is like a very, high-level Python example of like how you do something like this. You get maybe like a derivation path, have some sort of identifier, because I mentioned a little bit earlier, there's different parameter sets, and those parameter sets determine exactly the structure of the tree, run that through, SHA-512, and then basically from there, you basically run the normal, the Sphinx plus key derivation, which is about deriving this key, and then boom, you can do that itself, right? So, so you can still have sort of like a seed. Maybe you'd increase some of the parameters on the seed itself. You can still generate address deterministically from that seed. Just someone can't take a public key for you and generate more public keys because that's a one-way hash function basically. And still, there's no known, to my knowledge, pre-image attack on hash functions today, even though maybe some of them have collisions that are somewhat cheap. One thing obviously is blocks, right? So right now signatures are very small. They're 64 bytes or so, and so increasing the signature size to 3 kilobytes or so does cut down on block space itself, right? So even with optimized parameters, there will be sort of like a reduction in sort of like the effective throughput effectively. And I think maybe someone will talk about this a little bit later, but it's feasible that you can actually use things like Stark to basically do aggregation of several of these signatures into one single basically proof, right? So maybe you take 1 million of these proofs would be much larger. You can give 100 kilobyte Stark proof and then use that instead, right? Obviously, that's needs to be developed, but it's interesting as well because there's something called Picnic, which is one of the NIST NIST finalists, basically, and it was actually a Stark-based signature scheme. It basically just worked by sort of like having like running a PRF, a secret through a PRF, and then doing like a Stark proof, this thing MPC in the head, along with it, that showed basically that this thing was generated in a valid manner. So it seems like there can be some friendliness there. One other thing as well is like for example, for Stark, there's certain hash functions that are sort of like more quote unquote Stark friendly because they have a structure that lends better to the way they define like sort of like the what's effectively a circuit basically. So maybe someone would look into something like that itself to actually have it be a little more friendly. These are just sort of like ideas in the parameter space that may make sense in the future. But yeah, so some future work. I started dabbling on it because I feel like there's a lot of conversation around sort of like the what do we do in the philosophy or whatever else. But like this is sort of like a more I think defined problem basically, and we just need some code. And once there's code out there, people can actually start experimenting with this stuff. Look at walls, things like that. So it feels like maybe there's like a few bips here. I have the code. I don't have the bips yet. But so number one, sort of like a bip for this like NIST-compatible Sphinx plus scheme basically. It may have different parameters. I think that'd be a question for discussion with the community. Okay, do we just have one parameter set, or do we have one for like the average case and one for like the off-chain multi-party computation case basically? That's one question as well. You need something to basically allow people to like once again generate many addresses from a single seed. And one other thing I mentioned a little bit earlier is that that misuse overload factor basically that was for a single address, right? So you can still sign with a single address 1 million times more than you're supposed to, and you're okay, right? But then you can still generate multiple addresses from that. And then I know there's BIP360 as well. Maybe something around sort of like, do we have a slightly different top-level output key construction basically that may allow you to reveal this stuff, but then also go on the other end. And I have some code that maybe I'll release in the next few weeks or so. Basically, PuKey BTCD in place, and I work on basically implement some of this stuff as a prototype, just to show exactly what we're looking at. What do we need to do as far as the stack size? How does the derivation scheme work? How slow is signing, verification, and so forth. And one interesting thing would be also as well is that like if I was going to pack a block full of this stuff, what's the impact on things like block verification speed and validation costs, for the network and so forth. And that's it. Thank you. Any questions?
Can I ask one more? When you go to the second last Sphinx parameter slide, you said you
this
can
one?
do this one. Yeah. You can do billions or millions of signatures. We don't want address reuse for privacy reasons. So if we tune that down to thousands of signatures before the security drops, could we get the SIG size down significantly?
Yeah, you can.
Do you have a gut feeling how far?
Yeah. I mean, so for example, like in the paper, they have a 2 to the 10. Basically, I didn't include that just because like it's a fairly small number compared to this itself. But so that's why maybe there's sort of like a a small and a big parameter set. Small is basically okay. Like I know I'm probably not going to generate like more than 100,000 signatures, more than 1 million signatures. Basically, that's more reasonable. And then you have something for more reuse. But I think you can get this down to like 2 kilobytes or so. I would need to actually look at some of the parameters around that. And once again, like even once you have the signature side, you can play around with the overuse safety, which maybe trades off for increased signing speed. Increased signing speed versus the actual size. And if you check out the paper, there is like some code. They published some C code basically where you can plug in these numbers and spit out a parameter set. And there's some graphs, things like that. The paper is really dope.
I have one question about. So I understand that the allowed signatures, you turn that knob down, you'll get a slightly smaller. But one big part about this is like it's stateless, right? So the idea is I don't have to keep track of which parts of the bottom I used before. But it seems like in the Bitcoin use case, you have a pretty hard limit on how many stateless signatures you could ever make, because that's how much is in a block. Like whenever you're making a signature, you can look at previous blocks. I mean, that's a different assumption. Maybe you can in a hardware thing, but you could say like, so you'd know more about this. Is there a way to like have allowed signatures sort of decoupled from stateless allowed signatures, where like I can make more signatures as long as I remember, like I can make 2 to the 10 without thinking about it.
Yeah.
But I can also make 2 to the 20 if I make sure I look at all my previous signatures.
Yeah, I mean, so one option is basically just do something like Forest itself. And Forest is a similar thing because Forest starts to degrade a bit once you start to like reuse number of signatures. So you can say, okay, we don't actually need the hyper tree itself because we have a more conservative thing, and these signatures will be smaller because, you know, rather than, because, you know, number one, you already need one of these for the signature in general, right? So you basically like, I'll cut off the tree and basically just do this instead of all the other stuff. So yeah, you're right. So if you make different assumptions around like, you know, is 1 million actually necessary? Is 100 million necessary? You definitely can get them smaller.
Yeah,
and it's just, yeah, and it's interesting because if you look at the forum posts on the NIST, website, basically it's like a Google Groups, some people are saying, okay, well, should we actually give, you know, the users leeway around these parameter sets, basically? Isn't it better to basically have one parameter set and them not necessarily worrying about it? And the other thing is, well, if you look at like, maybe it's here. Yeah, if you look at sort of the way these schemes are named, I think there's one where it has like a Q at the end, and that one has like less security basically. So they were worried, okay, well, how's the user going to know the difference between SLH DSA 128S and Q basically, right? So maybe there needs to be just some messaging around that, and you know, would it be a different opcode? Would it be 2 opcodes? Is it going to take a parameter, and then you know that determines if it's, you know, one of these sets basically. So it's kind of like a trade-off between sort of giving users customability for their use case versus just doing the most conservative thing. If you want the most conservative thing, you know, you have a 50 kilobyte signature, and then you're done, right?
Because like in Lightning, which is the case where you probably want the most,
yeah,
you're already stateful. Like each time you're signing, you know what index you're at.
Yeah,
so
yeah,
like,
yeah, and like even on the commitment, we know what the actual commitment number actually is. Yes,
right.
you're
So
right
it seems
that.
like you don't have that. You may need a lot, but you don't need a lot where you don't remember your previous ones, I guess, and that might be it.
And so the other thing is like XMS by itself, they're like stateful versions of this basically. So you can have a stateful version of basically just this where you're sort of remembering the signature count basically. And for example, in cases like Lightning, the signature count is actually already in the commit transaction.
Right.
So you can extract it, right? So as long as you have that, you can even see it on chain and then, you know, do something based off of that as well. So
okay, cool.
Question around if I wanted to do multi-sig with Sphinx.
Yeah.
You know, I'm Binance. I don't want CZ just to be the only person holding the keys.
Yeah.
Is that well studied? Is it trivial? Is it needs a lot of work? Where are we at there?
Yeah, so that's definitely a drawback. Once again, because like it's just a hash function, there's no sort of like structure. For example, if you look at Music 2, the way it works, you can like look at the equations and like, you know, cancel things out, blah, 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 and it works basically because there's structure that's actually inherent there. This doesn't necessarily have that, right? So it'd either be end signatures or feasibly a, you know, a Stark proof of these parameters set that the end signatures were there, right? For example, imagine like I had a Merkle tree of like the end signatures basically, and then I prove, okay, well, you know, this aggregated signature is one of n of these keys or 2 of n of these keys or whatever else. So it seems possible, but you don't necessarily have that structure there, right? And so maybe this is potentially one argument for something like the lattice-based cryptography, which, you know, because there's more structure there, people can make more advanced schemes basically around, you know, things that you would expect public key derivation, you know, adding signatures together, you know, stuff like that, right? But if you wanted to go for the conservative, we already have hash functions, nothing else, this is what you get, but there definitely are trade-offs involved.
Actually, follow-up question on that. If you just do generic MPC on this type of scheme, you know, with let's say, you know, you actually have to do all those hash functions in MPC. Has people done this?
Yeah.
It's feasible, right? Like, I'm just curious.
Yeah, I mean, so for example, there was another pseudo hash-based scheme as part of like this competition called Picnic, basically. And Picnic is based off of just that, basically, right? And like it has like an MPC in the head component, which
Without additional assumptions. Let's say like you have to do standard, you know, generic MPC for Sphinx without Picnic.
That's possible. Like to me, like I feel like that's like Picnic basically. If are you aware of the way Picnic works?
Yeah. But that's entirely different signature scheme, right?
But so you're saying you want to basically do like a shared MPC to jointly derive a signature.
Let's say we just standardize this one, and you know there's opcode verify Sphinx, but there's no other signature. You know, Picnic is not in there, right? And then someone like Fireblocks has to go implement MPC for this.
Yeah, that seems possible in theory. I don't know exactly what right, because like, would you need to actually invocate every single hash function call using the MPC? Exactly. Yeah.
Generically, yes.
Yeah. So what would be the speed of that, particularly when you're generating tens of millions, potentially hundreds of millions of hashes, for this? So it seems feasible, and maybe you're saying those that really need this, they can have some scheme, they can accelerate over else. But yeah, so I wouldn't rule it out. I'm just not sure exactly what some of the costs would be around like signature speed and such.
I think, yeah, because for Starks and Picnic, I believe there's additional assumptions, right, over Sphinx.
You're right. Yeah, over Sphinx itself. Yeah, because Starks has the whole thing around like the threshold for sampling and stuff like that. Polynomials. Yeah.
So 2 questions left: Hunter and then Ava, and then we get lunch.
Hey, can you hear me? Okay.
Yep.
So, wow, really great presentation so far, by the way. Do you think that we should have like configure opcodes for like when you go to spend, like in the script path spend, right? Like, do you think that we should have configurable SLH DSA opcodes? And another question I have.
What do you mean by configurable there?
Yeah, well, like just being able to provide these kind of parameters.
Okay, yeah.
Well, and then there's also another question I got is, because I got a lot of questions for you, buddy. Is, do you think that we like a naive implementation of Frost would be like, or Musig 2, like would they map onto this? Just because like it basically be like a Merkle tree of hypertrees, and like. At which point, because SLX DSA doesn't support threshold signatures, right? So like you would probably need to map these other systems onto that. Except they also make use of like the linearity of signature, and so
I'm delivery 3. Like should you let a user put in like a bit string and parse out the parameters and then do like that? Probably not, right? Maybe you should have a few, right? Maybe that's the question. As far as like, can you do something like that? Like, not necessarily, right? I mean, so you could do something like I mentioned. You could just stack the signatures. I could have like a Merkle tree of the signatures and then require, okay, well, 2 of these are revealed, which are Sphinx signatures itself, but you don't have any of the structure, that you use for things like, key aggregation, Musig 2, things like that. All that's gone because like, it's just a big hash tree. That's that, and which is what makes it simple as well too, right? Because you're just doing this hashing a bunch of times. You can check out the paper, like it actually has some pretty good pseudocode around the way you like generate this address, which is sort of like how you identify which leaf and then so forth, and you just repeat that all the way up, right? So there is that simplicity there because it's just a hash function, and that makes it simple. So you do trade off that for flexibility.
Okay, thank you.
Thank you. I think Ava is saving her question for later, which means it's time for lunch.
Yeah.
Let's give a round of applause.
Thank you.
Quick question. All right, how many people here know where the venue is? We have D, obviously Alex, myself. The venue's up the street, but if you want like help finding it, find one of us. Alex, you might have more comments about how to get there.
Yeah, if you go out this side of the building, take a left up the hill. It's at the top. You'll see it. It's the very imposing building. 2 cannons out front, Presidio Officers Club. Lunch is in the back, all the way back and up to the 3rd floor. You'll see it. We'll be there helping. If you do me a quick favor, if you guys have dishes that you use, please put them in the kitchen, preferably the dishwasher. Throw out any trash. That'd be amazing because we'll be back in here tomorrow, and you're looking at your cleanup crew right here. So thank you in advance for helping out.
Last thing is